Go live here. Hopefully. Says we're live. Hello, YouTube. Some of you guys out there, let us know if you got the audio. I think you do. It looks like it. Joined this afternoon by Shaikey and Judy Bassett, Moyak, Rob Barton, and Tiny Captain. Hello, everybody.
Hello. Yeah, I can
Hello.
hear you good.
Hello.
Hola.
Hello, Big Blue.
Hello there, Alan Evans. And Peyton Asa Shield just joined.
Hey guys, how are you?
You.
Hey,
Well,
Shield.
thanks.
How you guys? How you doing, Shield?
Good. What are we talking about?
Well, we just started, so
Ah.
nothing. We were going to talk about you, but you're here now, so we can't.
I'm used to it.
Yeah.
Saw you in Geo's there a bit, listening to some of that nonsense.
Yeah, I was having a hard time getting a word in edgewise, so I just left.
Yeah, you're too nice. You're too southern. No.
Well, it was actually a Glober that wouldn't shut up.
Was it me?
No, not you.
Oh, I say, if it's me, tell me to shut up, and I'll shut up for you.
No, there was another fella in there that needed to talk more than I did, obviously. So that's okay.
My favorite was in there was hearing Witsit talk about airplanes again. For someone he's actually quite a smart guy, but he's really, how can you be so, what's the words I'm looking for? The difference between smart and intelligent, or intelligent and smart. I don't know. Because he seems to be a really smart guy, but he's got some really stupid ideas.
Well, it's that age-old saying, the scarecrow. Some people with brains do an awful lot of. Some people without brains do an awful lot of talking, don't they?
Oh yes. In fact, they do. Oh, Witsit's not dumb by any stretch. I think he's smart, without question.
Well, he was having problems with the fact that an airplane could go 800 miles an hour over the Atlantic, and you're going like, wait a minute,
That's ground speed.
Yeah, with a 300 and 200 mile tailwind.
Sure. Yeah, that's ground speed though. Not airspeed. His airspeed's 550. If you talk to the pilot, his indicated airspeed's something way less than that, But
well, then he was going, well, how do you measure ground speed? And going like, it's a couple different ways, There's a couple different ways to measure ground speed.
You can call up LA Centre and ask them, can't you?
Oh yeah, they'll give it to you.
Yeah. Over the Atlantic, it's a little tough, but yeah.
Yeah.
But in today's with GPS, almost everybody's got ground speed.
He was trying really hard to make it work.
If you dangled a rope with knots in it, you would just drop that behind the airplane. You would count the knots that fell through your hand per second.
I kept asking him, I was like, so do we not know the distance?
Right, that was wild.
Apparently we don't.
Yeah, apparently they get these airplanes, fill them with 500, 600 people, and take off, not knowing how far they're going to go.
Just hope for the best. Is that how it works?
Yeah, kind of.
Oh, interesting.
Fill her up. We'll see what happens.
Check your all, ma'am. Hey, guys.
Hello, Sean.
Wasn't that one of the airplane movies where the guy pops the hood and checks the oil in the engine?
Yeah.
Certainly was.
I streamed Geo's stream yesterday with Witsit and a bunch of people, and they showed him proof of Earth curvature with that Earth curve calculator without refraction, and he would not accept it. He would not even have it. He wouldn't even look at it.
Yeah, that was his latest thing. He's got this from somewhere in Corsica to somewhere just barely in Switzerland, excuse me. And it works. It works without refraction, and he wouldn't accept it.
Yeah. First, he got the place where he got the height wrong of the mountain, and then he said France. Sounded like a conehead. It's from France.
Well,
But it was from France. It was France. Turned out to be France, but it looked just like the San Jacinto mountain range.
Well, these are French guys. They're in Corsica, looking across Italy into Switzerland, I think.
Yeah.
Didn't he get the height of the mountain wrong too?
Yeah, he did.
Yeah. Of course, he was. Well, that was because he was in direct contact with the guy. Close contact. He knew exactly what was happening, but he got the height of the mountain wrong.
Well, the other thing he was doing was going from meters to feet back to meters, and you're going like, wait a minute, keep your units straight.
Yeah, and he actually got the name of the mountain wrong. He called it Mount Rose, but it's Mont Rose.
Right.
I was waiting for someone to say, words matter, Austin. Specificity is important.
Well, these guys were French. These guys were French, so they were using the French name, which is like Mastif to San Rose or something.
Yeah.
And then I heard when Travis wanted to come in and talk about
Travis is just a waste of space, man. He had nothing at all to contribute to that conversation. All he was doing was stirring up shit. I heard that. Yeah, I heard that part. Got that on tape.
And he blames you for taking his paper down.
Well, good. I hope he does.
He said he got an email from them telling them why.
It's just basically because he's a flat earther.
Yeah, he misrepresented himself and his position.
Yep.
Well, this paper didn't say anything anyway.
No. Well,
remember when he had that interview? He did that interview with that guy, and there was that part when the guy mentioned the curvature of the Earth.
Yeah.
And then he said something like, "Oh yeah, we'll come back to that."
Never did he?
Well, he claims he never said that.
Mm.
Is that video still on his
Oh, I've got the video on mine. But I've got the video of him saying it. I reviewed it, but yeah, he definitely said, we'll get back to that. He said, talking about curvature. He said, yeah, we'll get back to that, but first let's talk about this. And yeah, he had cleansed his background of anything flat Earth, made it look like he's just a normal guy and interested in science. And he took the paper that one guy wrote and kind of changed it a little bit and submitted that. That's what he submitted. So yeah, he was being very dishonest. And the guy he was interviewing is the guy that runs the website, but the physics department are the people that are in charge of the website. They're in charge of what content goes in, okaying everything. So
yeah, apparently this guy's like the retired head of the department, so he's got some rights that are like, because he's retired head of the department.
Yeah, but the rest of the department didn't know what he was putting up there. So they had a special meeting just for Travis and reviewed his paper, and his paper did not get peer review.
It was found wanting.
Yes.
Well, of course it was.
Your number one on his hit list.
In the subsequent paper, like they kind of mentioned his name.
It does have his name on it. I mean, the paper that was left, the original one, does have his name on it, but it just credits his photography. That's all it does. It just said, here's some pretty pictures.
Yeah. It also has a globe toward the bottom. I thought that was kind of nice.
Say hello to everybody out in the chat this afternoon.
Hello.
Not you, damn it. Shut up.
Oh, I thought you were telling us to do that.
No, I'm doing
Sorry.
it, man.
This is Blue's moment.
Time to.
Okay.
I'll mute him in a minute. Damn it, Sean. Yeah, let's see here. What was I trying to? Oh yeah. Well, we got Rob Parks out there and Clive Wells, Real Cygnus. Driver Dan, Navy vet. Lefty, Gorg Haynes. I already said Clive, I guess. Let's see, who else we got? Scoot, AT2 Productions. What's going on, Jared? How you doing, man? K Mac. Let's see. Who else I noticed up in there? If I missed anybody, I apologize. Stevie B, Mark 10. Tusk is out there. The Kitsune Cavaliers there. And Feral Cat, too. Hey, Cat, what's happening? And let's see, who else we got? Hads is out there. Tiny Captain's in here, too. Quinlan, 1977. How come you're not blue? Damn it. You can't be running around out there with no clothes on. There you go. Got you fixed. And there we go. I think that's pretty much everybody that's out there right now. Again, if I missed anybody, I apologize. Now, what other silliness is going on? What, did I kill it? Did I kill them all
have
off?
killed it, man.
I killed them all off? Oh, no.
We haven't heard much from Gary recently.
That's true. We haven't.
And
Don't
some
worry, I'm sure he'll be back.
Have not
you
heard
said
of
that
it.
was a bad thing.
Yeah, it's not.
He has no shame.
Oh, Gary loves us. Come on.
Oh, the one thing I thought was funny yesterday on the thing was Travis Finley, who pronounces everybody's name wrong. My name is Sean Yonquins, was complaining that Sean G was getting Austin's name wrong. I thought that was just fucking sweet.
Yeah. Yeah, he calls me, well, he hasn't called me in a while, but he used to call me B-Brick.
Yeah, but
He
don't
calls
you
everybody
dare
names.
play with his name because he won't like it.
He calls everybody names.
And he gets mad at me when I call him a magician. So, yeah.
Old Trav ass. He gets mad when I say that too. Oh, well, yeah. What can you do? Uh-oh, Clive Wells. Yeah, you're skating on thin ice out there, buddy. He's trying to whistle up Gary.
Quick, some cows are on the loose. We need somebody. We need a man for the job.
What's the movie that comes from? Oh, sorry.
We need a rubber band expert.
What movie is that from where you say the name 3 times into the mirror? What?
Beetlejuice.
Candyman.
Beetlejuice.
What?
Oh, Beetlejuice as well, but yeah, it's Candyman. In the original story, it's 5 times, but I think that
Bloody
I thought
Mary.
that was too long.
Bloody Mary as well.
Is it?
Yeah, but yeah, you're right, Blue. It is Beetlejuice.
Yep.
Oh, it didn't work.
No.
No, that
Chemo.
Apparently, there's
I will hunt you
It's a
down
sequel
and
reference,
hurt
huh?
you, man. Who said that?
Mabbit.
Stop it.
Oh, dear God.
No, not him.
This is out of control.
Yeah. Might need a reboot.
Yeah. Discord might have to have an accident here in a minute.
How's my mic? Does it sound terrible?
It's as
really
awful as
terrible.
ever, yes.
At times it's really
Okay,
shitty.
yeah,
but
I got my helmet on, so I'll be on mute for a while.
Okay.
yeah.
God, it's bad enough when he hasn't got his helmet on, blimey.
Motorcycle or army?
motorcycle.
Okay.
Not sure. Could be the Army. He is in the Army, you know.
I know, but usually when he says that, it's because he's got his crash helmet on.
Yeah. Yeah. Yeah, normally.
It goes from bloody awful to dire.
Well, I ran across some more quantum eraser stupidity there the other day.
Oh, God.
Okay, now everybody can use crash helmet.
And we might watch a little bit of that. Now, I think I'm having, before the show started, we messed around a little bit, and I think I'm having a few issues with the audio again, but I can fix it where you guys will hear the what YouTube is hearing as I play this thing. But if you talk, you're probably going to hear an echo. I think normally it'll be okay. But I think you guys can see what I'm sharing up there live right now.
Mm-hmm.
And I may just need to mute my mic. Might be enough. We'll try it. But first I need to switch this output. So now that's
Oh my God! Are you serious? Oh, I'm reading too. I'm sorry. Turn me in.
There's the you're in the echo mode now.
I'm reading what he says before you get to it.
Yeah, YouTube's not seeing it yet, so let me put that on the screen. I think I can do that, like that. So that's going out to YouTube now. We'll just listen to a bit of QE. I'm not going to stop it a lot. Let him kind of go through here and make a complete ass of himself, and then we can talk about it. So here we go.
What again?
Yeah.
All thermodynamics and Brownian motion. Then all we'd have is a single rotating non-inertial spinning reference frame. Now, how can that be when from Britannica.com says the Coriolis force, also called the Coriolis effect in classical mechanics, is an inertial force? How can you have an inertial force without an inertial reference frame? Por favor. I get that's the $64,000 question. Duh. You tracking yet, baltards? Probably not. You need to get your slobber nurses involved in this to help explain this to you.
Hey, Blue.
This is a joke. These are jokes.
It's really echoing.
Well, there's nothing I can do about it, Sean.
Okay, all right.
I'm very sorry.
Oh, no problem.
But I don't know how to fix it. Let's let it play and not dwell on that too much.
Right. So, and then you say, QE, we never said that. Oh, really? You never said that. That's interesting. What are you doing? Get up there. Getting angry with my computer. All right. Screwing up already. This might not go well, Betty. So, and like I said, you say, well...
You're being a hothead too now, huh?
It is.
Yeah, so that keep you cool so your computer can keep cool.
Damn insolence. It didn't want to put hillbilly blue balls around that retard up there. So, like I said, circling back, if you say, QE, we never said that. Oh, yeah, you did. Yeah, you did. You had a presentation. And I remembered it when I was going through this for the second time. That Flatsoid did a rebuttal video on hillbilly blue balls, and it was hilarious, right? And there was a lot of information in there, and we were only looking for a few bits. But something else popped up, and that's why I call him not only hillbilly blue balls a redneck retard, he's Mr. Gumby Football Field. We're going to get to that here in a couple minutes, but I want to stress this, that if they say they never said it. So, hillbilly blue balls. It is one non-inertial reference frame. That's where Coriolis takes place, not two reference frames. Well, how can that be? if you have only one non-inertial reference frame?
How can that be? QE, you're an idiot. Inertial forces only appear in non-inertial frames of reference. Inertial forces disappear in the inertial frame. What is wrong with this guy? By the way, are you guys able to hear it well enough?
Yeah, no echo now.
Yeah, it's a lot better. Yeah, the echo's gone.
The echo disappeared.
Okay, that's I muted my Discord mic while it was playing, so I guess that's what I got to do. I don't know why, but whatever, if it works. But anyway, you see the problem with QE here. He sees a thing called an inertial reference frame, and then he sees something else that's called an inertial force, and QE very wrongly believes that those two things have to go together. How could you possibly have an inertial force unless you have an inertial reference frame?
Oh, man.
Yeah.
It's sad. It really is. Well, what's really sad is the number of people that that guy has managed to bamboozle with this bullshit. And this is exactly where Nathan Oakley and the rest of that mob, plus others all over the internet, get their information from. They're listening to this half-wit. Poor excuse for a cook.
Yeah, the saddest part is the gullibility of his listeners.
Yeah. Who claims to know something about physics when clearly he doesn't. This is just fundamental, and I really can't. I can't understand why people listen to him when we have told them. Not just me, lots and lots and lots of us have explained this over and over and over again, and they just don't want to hear it. They want to believe that QE is somehow or the other has some knowledge here. I don't think so. Well, let's hear some more of it, I guess.
And the Coriolis force, as we just read from Britannica, is an inertial force. How can you have that without an inertial reference frame? Hillbilly? Please riddle us that, Mr. Gumby Football Field. Now, when I went down and chased this in Flatzoid's video, now this is a Flatzoid video of Hillbilly Blue Ball's video.
Back,
so if you go back to that video, you're going to hear Billy Blue Ball say those. That's why I put the quotations around this one up here. All right. So if you go back there, but while I was back there, I seen something else. It was quite disturbing. And let me share it. This popped up on the screen because I guess he was trying to somehow deconstruct or straw man Neil deGrasse Tyson's argument, about the football. You guys all know this. But I seen this flashed up for a second, and I said, wait a second. Let's take a look at this. So Hillbilly Blue Ball says, you got a little arrow up here. You see the football going through the goal. He says the Earth's tangential speed at the goalpost is 1181.4727 feet per second. And then he has another arrow saying that the Earth's tangential speed at the 40-yard line is 1181.4831 feet per second. So this is the disturbing part. I don't even know if it's batshit insane. Not only does Hillbilly Blue Balls think the football field's moving, I mean, that's bad enough. But he also thinks he's got a Gumby football field. He thinks the goal, where the goalpost is moving slower than the 40-yard line.
Well, I think that for a reason. Because it is. Jesus
Yeah.
God. It actually is. The tangential speed is different. This is a field. This is the example that Neil deGrasse Tyson famously used about whatever game it was. And the field is oriented north and south like I've shown it. Well, quite clearly, the goal line is going to be moving a little bit slower than the 40-yard line is. I don't know why they have a problem understanding this.
Yeah. If the football field was, I don't know, 6,000 miles long, and that goalpost was at the North Pole, yet the tangential speed of the goalpost is going to be 0, and it's just going to get faster and faster the further you go toward the other goal.
Don't understand it.
Nope.
What latitude did you put this at? I did something similar. Came up with 8 millimeters, which is slightly different. You have 9.5, but the further north you go, the worse it is. As you said, it's worse if the goalpost was exactly at the North Pole.
Oh yeah,
which
sure.
Which side of the goalpost the ball went? Left or right? West or
It went to the right.
It goes right because of the
It hit the left. Of course, it hit the left upright, if I remember correctly.
Of course, there's wind and the kick and the snap and the rush and a whole bunch of other stuff. It's going to be a whole lot greater than 3/8 of an inch.
Neil deGrasse Tyson was just making an interesting story and an interesting way to describe to people, what Coriolis actually is and what it could do.
I wonder if he knew when he did this that it would be famous among the flat Earth community, or if he just sort of offhanded it.
I doubt
thinking this would just be a throwaway line, because this has become a major concern problem with the flat earthers.
Yeah, it has.
It's going to be a shock to them if they heard that we actually in merchant sailing also use the Coriolis effect.
Oh boy.
Well, the amazing thing is, of course, that QE doesn't know the difference between the issues of relative velocity. Because I think in this same thing I saw this, and I was going to make a video about this stupid thing we did recently, but difference between relative velocity, i.e. the Earth's rotating at all, and the Coriolis effect. He and Nathan Oakley says this all the time. He gets confused between the 15 degrees per hour and the effects of Coriolis, which of course are just related to a velocity with respect to your inertial reference frame. So they haven't even got on the first rung of understanding what this is. And I bet you that QE didn't understand the north-south thing that you did here, because I didn't immediately. I only saw the picture that he put up, because you don't mention in the thing there the Earth's tangential speed at this latitude and then this one at this latitude. But you put the north-south in there, and of course he doesn't, I suspect, understand the significance of the north-south orientation.
Oh, the American football fields tend to be aligned north-south so that the sun doesn't get in your eyes.
Yeah.
Oh, really? Oh, okay. Yeah. Oh, right. Okay.
Not 100% true, but as a general rule.
It's not, but everywhere they could, that's the way they tried to align them.
Right, but I bet you QE, if you asked him if it was on its side and you were looking along it, whether that would be true, I bet you he wouldn't know the difference. He wouldn't understand the issue.
Probably not.
I mean, we're dealing with a moron here. I say he doesn't understand just between Coriolis and the rotational velocity of the Earth. He doesn't understand those two things are different. I mean, well, he's a moron, isn't he? I mean, he's a malicious moron, so.
Yeah.
Well, I was trying to explain to Whitson, we were talking to Whitson in his aviation, that he knows nothing. He's stuck on this 800-mile-per-hour airplane and saying, well, why do the jet streams go eastbound?
In the same, perhaps I don't want to perhaps preempt you, but he makes it clear that he doesn't understand that physics works on a train. If you're going on a train at 200 miles an hour, I think he says something later on where he doesn't understand that relative velocities are important. That you can't measure anything different in physics if you're going at a different velocity. He doesn't understand that who's echo? Is someone echoing here? Or perhaps it's the stream. Perhaps I need to mute this stream again. I think it's coming. Yeah, I think it might be coming through blue. Yeah, okay. I might have to do this muting of the stream that I did last time to try and clear that up. Yeah, he doesn't understand that on a. I think later on. Sorry to preempt this, but he doesn't understand that you can basically throw something up and down in a train that's moving at 200 miles an hour on Concorde, and it will all work. Anyway, that's probably for a later point. But the guy's a moron. I mean, the guy's a moron, a malicious moron. So yeah, Blue.
Well, I'd like to invite you all to play a little game I play when I fly in airplanes. First of all, I get to go to the front of the airplane. I make sure the aisle's clear. And then I jump up and I slam against the back at 500 miles per hour. It's a real fun
exactly.
game.
Yeah, you be careful doing it. You'll hurt yourself.
I just
exactly. I think they don't understand this. I really think that they don't understand this simple issue that, pouring yourself a cup of tea on an aeroplane or on a train, that it falls vertically. I can't remember. There's something later on they do with a simple experiment that the QE demonstrates. He doesn't understand that simple point that if you to jump up in an aeroplane, as you say, you'd hit the back. He doesn't understand that you've got the velocity of the aeroplane and you're not going anywhere. These people are so stupid. I mean, this is something. What age do we? I mean, I think I probably understood this when I was about 10. No, must be earlier. I don't know. It depends on when they've given a question. I suppose I'm thinking when I was given a question on the subject at school, whether I would say, you carry on at that velocity or not. But when I understood it sort of in terms of intuitively as a child, I mean, you're probably thinking about sort of 6 or 7. And these people don't understand it, and they're adults.
Yeah.
We had kids. I used to skateboard when I was a kid. That's when skateboarding first really started taking off back in the 70s. And I was part of a skateboard team. Oh, wow. That was a real thing. They did high jump, long jump, where you skate up to an upright, like a high jump bar, and you jump off your skateboard over the bar and land back on your skateboard. If you wrecked, or you knocked the bar down, you didn't get a point. And there were kids who couldn't understand they didn't have to jump forward.
Right.
They try and jump forward, and that board would, shoot out from behind them, and they'd fall. I knew back then that at an early age that conservation of momentum is your friend.
Well done, Sean. In fact, on this point, there's a classic demo by oh God, who's the Dutch guy for MIT? I've forgotten his stupid name now. Who does these videos? And he's got this traveling on an air trolley thing in a physics lecture. I've forgotten his, I can't believe I've forgotten his name. Yes, and he shoots a ball up. There's this little trolley thing on an air rider thing. Shoots a ball up, and then it carries on. So it's moving along. It shoots the ball up, and then about 20 feet later, it shoots up about 30 feet in the air, 20, 30 feet in the air, and then it lands right back on the thing as it's moving along. It comes back and lands directly back on this trolley thing. It's got a little funnel on the front of it, and it carries on and then jumps back in as a demonstration of the conservation of momentum. It's a fantastic little video at the end of his lecture, and I've forgotten his stupid name now. Walter Lewin lectures. That's the guy, Lewin.
Is he the old British guy that just?
Yeah, he's Dutch. He lectures at MIT. I think it was MIT.
Oh yeah.
Okay.
Yeah.
Walter Lewin, I think it is. And he does a series of lectures on YouTube. He covers the whole of his course from electrostatics to electromagnetism. I don't think he does quantum. And he's got this fantastic demo of this thing going along an air trolley. He just pushes it, and it gets up to a certain speed. He presses a button to launch a little ball vertically, and the ball obviously carries on with the constant motion and then lands back on top of the trolley. It's a demonstration that presumably QE doesn't understand, and half these bloody flat earthers.
He actually got famous, the Walter Lewin, with the ball that he actually let go just in front of his face and stand at the wall. Doesn't touch him anymore. Yeah,
that's the one.
Guy.
Walter Lewin.
Yeah.
Yeah, he's very.
Sounds an awful lot like Julius Sumner Miller. He used to do a lot of experiments with toys and physics.
Well,
stuff.
this is actually a lecturer. I mean, he's actually a university lecturer teaching. I think it's MIT. I can't remember. It's one of the East Coast top-notch. It's either MIT or
No, it's just MIT. Yeah. That's where he teaches. He's a physics professor at MIT.
From The Hague.
Quite famous guy. He's been around for a long time.
Yeah. QE Delft. Yeah.
Let's listen to QE a little bit more.
At first, I thought you were talking about the old crotchety, white-haired guy that speaks at the what do you call it, the Academy of Sciences. They have a whole series of lectures. They're like 2-hour-long lectures, and he gets mad a lot. He's got a very good sense of humor.
Twisted reality, right? Take this in, folks. This numpty dipshit, right? This is a slide. There's no way around this. He thinks he's got a Gumby football field with different parts moving at different speeds. Now, if I showed this to a mental health professional, you'd be through. It's all over for you. I mean, this is batshit insane.
There's another one that believes this too. I think that is it the Neil deGrasse Tyson thing that sort of is the same way.
I
think that's what he's showing the calc for.
Go ahead.
But that's fine. It's absolutely fine. Have it. Take it. Take that effect. Put it on an aeroplane. This is what they try to describe, this differential Coriolis. But this is over the length of the football field. And you can see what we've got is a differential from left to right of 0.3 inches, just over that very short amount of time. If I'm keeping my tangential speed, whatever that is in relation to things, but I'm flying north to south, is there a point where when there's a latitude difference of, say, 300 miles an hour, the equator to, say, 50 degrees or some 40 degrees, am I suddenly now coping with that? Because that's the claim here with the football. Stuff moves, hence the field goal is scored. Therefore the runway would be moving, but not just by this small amount now in the differential in the tangential speeds that he's calculated, but by the differential in the tangential speeds over thousands of miles.
Well, yeah, if you teleport from one place to another, sure, but it takes time to get from one place to another, and it just evens out. You don't feel it. Too gradual a change.
And also, did you hear him say, this is the other idiot, Adam Meakin, absolute moron of the first order, who said differential Coriolis.
Yeah.
You see, he doesn't, again, understand the difference between the difference in the tangential speed and what Coriolis is.
Right, exactly. But he mentions
go ahead.
He mentions if an airplane has to deal with that. Well, yeah, certainly it does. Not a question. But when you start talking about, think about this. If I started a flight, a theoretical flight from the North Pole, and I want to fly down to the equator, right? I start out with a tangential velocity at the North Pole of 0, and I'm going to have a tangential velocity of 1,000 miles an hour when I reach the equator, right? Everybody agree with that? Yeah.
Yep, absolutely right.
How long is that flight going to take?
15 hours.
Okay. 15 hours, 1,000 miles an hour over 15 hours. That's how much per hour?
Yeah. And if you look at, I've done the calculations previously. It turns out to be something like a quarter of a mile an hour increase in velocity. In other words, it's less than the acceleration you get getting out of your chair, or a slug. A slug would do some similar acceleration when it gets on the move. It accelerates to a similar level. You've got to increase yourself by a mile an hour over a mile or something. It's incredibly slow. 15 hours over that time.
I mean, a very rudimentary transmission is taking a cone as one of the drive gears, or as the follower gear, and you just drive a belt on it. If you go at the narrow end of the cone, you get a slower speed. If you go to the thicker end of the cone, you get a faster speed. So, I mean, I don't understand.
Well, the other thing they don't understand is that airplanes are not ballistic objects. on a ballistic object, you have to make all your corrections at the very beginning because you have no other inputs into the damn thing. So if you were firing a cannon from the North Pole to the equator, you'd have to take all that into account. But we're not. We're flying an airplane.
I mean, it would affect it to some degree, because the difference here is that an aeroplane, when you're going from the side, so if you'd making the journey that Blue was describing, you've got all the side of the aeroplane picking up the tangential winds, and so it will pick up the wind, the tangential velocity of the atmosphere as it goes along. But if you're firing something that's very heavy, like an artillery shell, that's very dense and small, then it will not be picking up the atmospheric drag so much. And so, as Paid Nasashil said, you would then have to take it into account. You still have to take into account to some degree, and this is why with firing systems like when World War I battleships, they first introduced these firing tables that included the Coriolis effect. You do have to take into account if you're firing over 20-odd miles or something, but the effect is much less than on an aeroplane, which has got a great big wide side to it, like a 747, that's obviously going to pick up a lot of the tangential speed, and it's not being resisted like the thrust and the drag are. It's just going to move along unless the pilot decides to do something about it. So yes, there's a big difference between a ballistic trajectory and what an aeroplane is, particularly because of what a ballistic thing is and what an aeroplane shape is.
Well,
0.0008 meters. That's what, just a millimeter per second?
Yeah.
8 millimeters per second?
8 millimeters.
No, this is like
it's next
they were
to
talking
nothing.
about,
And it's absolutely no problem for the guy flying the airplane who is even if you're hand flying the damn thing, people don't understand what you're doing. All you're doing is trying to keep yourself over the top of a track across the ground, and you're either deviating to the left of the track or to the right of the track, or you're right over it. No matter what goes on, you make whatever correction you need to stay over the center of that ground track. That's how we fly. That's how airplanes work.
And you did the calculations yourself, Blue, I remember, and I agreed with them completely, where we worked out what the acceleration would be due to Coriolis. And it's so tiny, it's much less than any wind or any waft of air going around. It's so insignificant that you just couldn't even measure it. You couldn't even take any action to correct for it. It's so small.
You'll be correcting for it, but you'll never know that you're doing that because the other influences swamp it completely.
Absolutely.
The lightest wind I can imagine is probably 50 times as much as Coriolis is.
But still for airplanes and for ships, a Coriolis effect is an important thing, but not what you think of. It's not for the flight itself. It's actually the weather.
That's right. That's another point they religiously miss. We owe the winds aloft things like those prevailing winds and jet streams and stuff are directly a result of Coriolis force.
And that's the part that when I say that, it blows their minds that yes, we have to take Coriolis into account because Coriolis is the main cause of the winds in the world.
Yeah,
if the Earth were stationary, we would be heating up the air down at the equator more than any place else. And that air down there would flow toward the colder regions of the poles. And we would always have that sort of flow pattern.
Correct.
Always. And it would be
so
north
the Coriolis
to south,
just simply
not
changes
east
it.
to
Yes,
west.
you still get the wind flow, but the Coriolis changes it with respect to the Earth's surface.
Right.
There's also someone, by the way, in the chat claiming that World War I battleships did not include Coriolis. Oh, yes, they did. At least all the information that I've got, that's when they first included them. And there was even a point at one point in the Battle of Falklands where the claim was that because they were in the southern part, the southern hemisphere, they had the Coriolis calculations around the other. They didn't include. They were negative instead of positive, and therefore there was a cock-up. Although there has been some suggestion that wasn't the case, but nonetheless they were worrying about Coriolis on World War I battleships.
Yeah, but the main thing we use now in merchant sailing and also on airplanes is actually we use the Coriolis effects to calculate how we can avoid tropical storms and hurricanes.
Yeah. More significant
the wind itself,
for
as
you,
Blue said, is caused by the temperature. Go ahead, Blue.
Yeah, it's more significant for a ship captain, I think. He's going to be more because it's going to have we can get around that very easily and quickly in an airplane. That's not necessarily, that isn't true at all, I guess, with a large ship. You're not going fast enough to get out of the way of things. You need to be able to predict what's going to happen.
No, and especially because I'm mostly in towing jobs or delivering a little bit smaller ships. They are very slow.
Yeah.
Because one thing, of course, we all know. I think Blue, we know this for a fact. They don't know what the formula is for the Coriolis force. You can guarantee they've never looked at that. And they certainly don't understand what a vector cross product is.
Right.
Which is part of it. I mean, it's so far beyond their understanding, it's just not even worth bothering to try to explain them vector cross products, I think.
I know. That just puts their heads spinning around in circles, you know.
Yeah, I mean, they just go say, "Oh, well, that's just gibberish," or "I don't understand that, therefore it can't be true." The trouble is, when you got to think down to these people, and so if you give them an explanation of actually how the real world is, they're not going to understand it. So you've got to go several steps down and give them the simple sort of childlike explanation that they give to primary school kids, and then see if you can then hold on to them, get them to understand some little bit, and then gradually build it up. But unfortunately, that takes minutes or longer, and not, and particularly if they're willfully ignorant, of course, they're not going to want to understand, and this stuff is just beyond them. Unless if you've got them in for a couple of days, I mean, we're basically tutoring these people. If we could get a QE for a week doing a little bit of maths, you might be able to end up with him understanding what a cross product is. I suspect, possibly. Like, if you're lucky, there's no way he's going to understand it from his own research or in terms of being engaged in a debate.
You kidding me? The guy can't even do arithmetic.
Yeah,
I proved that.
I mean, Blue, did you see his I mean, this was about three years ago. So, I mean, his classic calculation of how much dip an aircraft would have to go around the Earth, and he just simply took a distance like 1,000 miles away, and they said, "Oh, well, it's going to go." It was the most pathetically primary school, and they also Adam Meakin did exactly the same calculation as to how much dip he thinks you have to do, not understanding, of course, that if you do an instantaneous following of curve, you don't have anything like that a rotation, a dip, as he put it. I can't go into it now, but he used the most pathetic primary school construction of triangles along with Adam Meakin to try and understand what an aeroplane actually does as it goes around the Earth. And of course, he's an idiot. He doesn't even understand how to do simple things like, I don't think he even understands trigonometry. And of course, remember, this is the guy, I think you, Blue, pointed out this out. He doesn't understand that 10 to the minus 17 is not a negative number. Or what was the other thing? I mean, this is an idiot. I mean, we're dealing with an idiot.
Blue made a video about this. He couldn't add the numbers.
Yeah, he couldn't add. I can't remember exactly what it was now, but if you could remind me what it was he couldn't add together.
I forgot
10
now.
10 to the minus 17.
I think it was 10 to the minus 17, wasn't it? He didn't understand how to do that.
Subtracting one.
It was two pressures subtracted.
Yeah. Yeah, and there were too many zeros to fit in his calculator, so he tried to do it by hand. And he subtracted one number from another number and got a bigger number.
And of course, he doesn't understand that being very close to a vacuum, part of this problem, I think it might have been in the same video, where he thinks that there's a big difference between the difference, he doesn't understand the pressure difference between, say, if you want to work out the force acting on, say, the hull of an aeroplane, you just take the difference between, say it's a vacuum outside the aeroplane and inside there's pressure of 8 psi or whatever, then there's a pressure difference there. And he seemed to think that if it was not quite zero, that was significantly different to it being zero outside. And again, this is all part, I think, of his inability to subtract numbers from one another. I mean, the idiocy is everywhere, and so basically there's so many things you have to try and explain and cover up. These people who misunderstand everything they can get their little hands on, and so it's like fighting off a fire from lots of different directions. Which one you choose to put out first? It's extraordinary.
Well, I've seen quite a few of them that have that same
Yeah.
the same problem, understanding that
It could be.
There's
Perhaps
absolutely
that's the thing.
There's absolutely no difference in going from 100 psi down to 99 psi than there is going from 1 psi down to 0.
Yeah, I wonder if they understand
no
that.
difference.
Do you think what a chance of them understanding that? I wonder. That'd be a really good quiz question, actually. That one. That's a really good way of testing their basic understanding. Perhaps you could start off if you had a debate with them, quiz them with that one. Yeah, that's a good one, actually.
Yeah, they have some wild idea that for some reason there's something magic about a really, really small number. No, There's nothing magic about it. It's a 1 psi change, period. It doesn't matter where you start from, it's still 1 psi change.
I think they think maths is magic. That's the problem.
Maybe. Well, I've only got about 3 minutes of this left. Let's just torture ourselves and blast through this, and then we can relax and laugh at the fools.
Which would mean the runway's moving sideways at 300 miles an hour as I come to land if he's going to apply this non-supported piece of just mathematical calculation. But that, if you're going to have that, it has an implication on everything.
It has an implication. It has an implication with mental health services.
Well, I know, but that's why you do need mental health, because it's really that what you believe is happening. Because if you think it's happening to the ball, it's happening to drones, planes.
Yeah. Don't lose the point here. Hold on a second. Oh God.
I want to say this. I wonder if he finds his way home. Ever.
That's what you had?
Yeah, that's what I had. Profound.
Stop, you two guys, stop ruining the point. Even though you're all correct.
Every time Betty speaks, why do I think back to the days of Saturday Night Live and that phrase, "Jane, you ignorant slut," comes to mind.
Yeah, exactly.
Only in this case, it's Betty. Yeah, I'll stop right there.
So
all she has, she's like Travis. All she has to offer is
doesn't matter.
Just mockery.
The person next to you, just tell him, do you know that this field is moving? Not only that, where we're at, and you see where the field goal post is, or the soccer goal is, or the outfield is, that's moving slower than we are. Just say that don't lose this. Keep it simple. Utterly. This is so far beyond batshit insane. Right? So, like I said, that's what I wanted to leave everybody with. When next time you see this hillbilly, is he still out here?
Probably.
Well, anyone run into him, ask him about Mr. Gumby football field. See what he says. Okay? Get out of there.
Maybe he has a medical condition called vertigo.
You think? All right, back to the point. I just wanted to stress that, Mr. Gumby football field. We're back to the point of these gases. Like I said, at first, that's the least of their problems up there with the two separate reference frames. With the air traveling with the Earth, they got many more problems. And it's bad. Number two, if you believe that, show the experiment where gases rotate in lockstep with a rotating solid body just 5 centimeters above the surface. Then provide the mechanism. I'd like to see that. You do understand that gases have no intermolecular bonds. Obviously rhetorical. So do gas molecules attach to the Earth and each other by Velcro, superglue, molasses, pixie dust, other? And gas molecules, that's air, vibrate and move freely and randomly at high speeds. Let's check this out from the chemistry department at Purdue.
No, I don't think so. I don't think we want to check that out, QE. My God, what an idiot.
So he's calling you Gumby football field because he thinks that the field is bending?
Yeah.
I guess.
I mean, he doesn't understand anything.
Yeah, I mean, basically, he doesn't understand net movement. When I had a debate with him about 3 years ago, the only debate that he's ever had, I think, with a Glober, except for that nice guy, the teacher guy, what is it, Flat Earth Math or something. The only person he's ever been, he's ever bothered to debate since, after he had his bad experience with me, brought up this subject of he didn't understand, for instance, you could just argue how he was saying there. How do you have something moving as a rotating body and have all these random movements at all? Well, then you can ask yourself, what's happening if I get a bath and I put it on a lorry? Do the molecules inside the water inside the bath full of water, I mentioned that, stop moving randomly? No. Are they moving as a net macroscopic movement? Yes. They're doing both. There's a net movement of the body, of the bath water, and all the molecules are still doing their own random thing. You can have them together. So basically, this is an argument I tried to get through to I can't remember when I might have been part of the debate I had with him. He didn't understand this. He rejected this as I might have been interrupted sufficiently. He may not have got a chance to fully, but he doesn't understand that concept that a moving bath with random moving molecules in it is a thing that you can have, and the atmosphere is much the same thing, and that's completely beyond his understanding. As you can see here, he's just abusing Blue for his own stupidity. I mean, this is the Dunning-Kruger writ large and delivering abuse to those who do understand something, just basing it on his own ludicrously inflated opinion of his own understanding of basic physics, which obviously is zero.
Oh, Rambus, just to annoy you. A non-moving liquid does not exist. Because if it doesn't move, it's actually a solid.
That's right.
And even solids are vibrating.
I mean, there's exercise. There's experiments that I've seen where they take it's a fluid, a little thicker than water, more viscous than water, and they put dye in it, and there's a ball in it, a sphere, and they rotate the sphere, and the ball, the dye, the paint moves with the ball.
It will.
I think he thinks that molecules that move at high speed in all directions means they bouncing in your room from one wall to another. That's what a air molecule does, doesn't it?
Do you know what the mean free path is? You know what that is?
Yeah.
Of course you do. The mean free path down at sea level is what, nanometers. It's a tiny, tiny difference any molecule can move before it bangs into another one.
That's right, but bear in mind that the ideal gases are based around the fact that most of the time gases are not actually interacting with one another. So although the distances between are very small, let's not forget that atoms are also incredibly small, and they spend most of their time, even in a gas which has got, billions of these things in a 24 liters. It's got 6 times 10 to the 23 of these. 1 mole is 24 liters, I think. Or was it 2.4? Is it 24 liters, 1 mole?
Yeah,
so that's 6 times 10 to the 23 atoms. They're missing one another for most of the time.
Yep.
So, although they might have a tiny distance to hit, they're spending an awful lot of time missing
not
one
hitting
another.
anything. Yeah.
Exactly. That's what they spend most of their time, not hitting one another. And that's how we model an ideal gas. And the atmosphere we have around us very closely models an ideal gas, i.e. most of the time the molecules are not hitting one another. Yeah, I mean, this idea that he doesn't understand. Someone in the chat was saying the Earth is moving in 5 directions. No, this is something else that flatties don't understand, is that all velocity vectors add up to 1. So although, if in other words, it's like pulling on an atom with 5 different springs or 5 different ropes, and you're all pulling away with different forces, the net force on the molecule is just one direction. Now, it might not necessarily match
a rope to a molecule?
Say again?
How are you going to tie a rope to a molecule? That's just silly.
Right, okay. Sorry for adding. Well, they have electrostatic force, but obviously with molecules, they're not. I was just describing this general language. It was just someone who was talking about the Earth moving. This general language, and SE Montreal had this problem as well. You often hear some flatties say, "We've got all these 5, 7 vectors," as though something that's being subjected to these 7 different directions would be jiggling like crazy, and we'd all be getting a headache on the Earth, as though it was all jiggling around. No, they're all results in one net direction, one force, one velocity vector. All those things add together with vector addition into one direction. So you could have 1 billion different forces, 1 billion different strings pulling on something, but ultimately you'll only ever have one direction as a resultant of all those forces or actions. Okay.
That's right. You'll have a resultant vector. You can start with that resultant vector and deconstruct it into all of its constituents. if you like. You can do it that way. But at the end of the day, unless the thing is coming apart and flying in different directions, you don't have multiple different velocities or multiple different,
The Earth's bulge, for instance, the tides are a function of actually what you're describing there. We have slightly different velocity forces on the one side of the Earth and the other, and then you get bulges as a result of that. So some parts of the Earth have very slightly different forces acting on them than the other, and so you do on the Earth do get slightly different forces, but they are, if it was solid, but even the solid Earth actually moves up and down by a foot or two as a result of the motions of the moon and things. But fundamentally, with what you called solid body physics, then you think of the thing as just one homogeneous thing that's just occupying its rigid body kinematics. Then it all moves just even if you put a million different forces on it, you just get one result.
Yep, that's all it can be. Can't be anything else.
But so many flat earthers don't understand that. They think, if you've got 7 different forces on you, you'd be somehow jiggling like in some sort of high frequency jiggling machine or something. Particularly mathematical with gravitational forces, of course. It's not like as though every atom in you is subjected to the combination. It's not like one part of you is subjected to a different gravity. It's not like your arm's being pulled or some part of the Earth is being pulled differently to another part, unless you get what I talked with the moon, local things. Every little object has the sum of those forces on it. It's not like one part is being pulled and it has to pull another bit and another bit has to pull another bit. So you get some sort of stretchy thing with gravitation. That you just get that one force acting, on everything individually.
I think that even if you were wrong and it was jiggling the way they say it's jiggling, you're still talking about totally insignificant values, like 1 degree per 1 million years around a galaxy. That's kind of not much of a jiggle.
Well, we're going fast, of course. The thing about force is it's related to acceleration. And although the sun is obviously pulling us with a much greater force than the moon, but we're going in almost the orbit of the Earth is almost a straight line. Almost. So that's why we are much more affected by the rotation of the Earth. In terms of the centrifugal force in effect. So that's what we know, 0.3% lighter at the equator. So the spin of the Earth is much more important because the curvature of your path on the Earth, at the equator anyway, is considerably greater than the curvature combined with the speed. There's the combination between there's omega squared r, so where r is the radius of curvature. But if there's something like from the sun, the radius of curvature is so huge that you're almost going in a straight line, so you can almost ignore the centrifugal force of the sun. It's about 1/50, I think, of the centrifugal force of the Earth, so it's insignificant.
Hold on. You don't care about the centrifugal force of the sun because that's a free fall. You're never gonna feel it. Doesn't matter how fast you spin around the sun, you will never feel it. It's free fall.
It's counteracted, yeah.
Well, hold on. Just like you get a loss in weight if you go from the poles to the equator, you can say what would be the difference between. You could one side of the Earth that's away from the sun, and the other side that's nearest the sun. So the radius, the diameter of the Earth, there is a difference. There is a slight difference between the centrifugal force. You wouldn't be able to feel it, obviously, yourself. But if you can measure the difference, I believe, between the centrifugal force at the far side of the Earth from the sun and the near side of the Earth to the sun. There will be a centrifugal force difference there.
No, it's a free fall. You don't feel it. You closer to the sun. You move faster. That you have faster tangential speed. Right, but the sun pulls you.
I'm comparing the two.
But the force of the sun pulling you is greater. This is a free fall. You don't feel anything. It's not something you can feel.
Well, that's like
if I set you in an orbit around the sun, 12,000 kilometers, 20,000 kilometers from me. I'm at the North Pole, and you at the South Pole, we will have the same orbit almost.
Well, that's where you wouldn't, because that's what causes tides. If what you said was correct, then you wouldn't have tides, because you could say that we're effectively in free fall with the moon, and there's a difference between the two, and the sun causes tides as well, and therefore the sun also causes tides, which means it's not the same at the far end and the near end of the Earth. Otherwise, there'd be no tidal effect of the sun, would there, from what you're saying?
It adds about 20%, isn't it, to the Earth's tides? That's the neap and spring tides, are the adding and subtraction of the sun.
Yeah. So if what you said was true, Chike, that there would be no tides due to the sun if everything was equivalent. Anyway, perhaps you can think perhaps we could have a hangout on that. I mean to do a video on tides and suns and things, and a proper one, because I don't think there have been another number of poor explanations, in my opinion. It's quite a complicated issue.
It has to do with that actually the forces of attraction are going in many more directions than people think. It's not going in one direction. Only most directions are cancelled out because the other forces are equal or stronger.
And if you get into tides, of course, and you get this issue, the fact that everything's delayed. I mean, you quite often see another flat earther argument is about tides. How come they don't agree? And of course, there's a delay in terms of the water and when the water is raised, not when the sun is directly opposite
it has to,
the Earth.
No, of course.
It's friction.
There's inertia in the system, and what's more, then of course you get all these flows around land and things have got to get out the way, and so in fact there's almost no. I think it's correct. There's almost no relation between the time of the sun at any particular part of the land and where the position of the sun is with relation to you of when the tide is. It's very complicated.
It has a relationship, or else we wouldn't have tight schedules.
Yes, okay. It's you can't work it out just from the position of the sun because of these inertia in it, and it's not like the sun. It's not like the water is attracted to the sun, then keeps on facing the sun. In other words, or the moon.
No, it has to do with way more. But there are tide tables that actually explain that all.
Indeed, yes, and they have to allow, obviously, for all sorts of it gets incredibly complicated.
And you get to fluid dynamics where you've got water, you've got this bulge flowing, and as it flows around land, it's incredibly complicated due to drag and friction and inertia, and it's really complicated. Here in New Zealand, we have the current, the way the tide flows right around us here is quite unique, and we have pretty much high tide somewhere at any time, because the way the bulge flows around, and it's all to do with fluid dynamics, and it's incredibly complicated.
Yeah. If you want to see real strange tides, you have to look at the north of Mauritius. They actually still can't calculate it there. Mauritius.
Say again.
Mauritius.
Mauritius. Oh, Mauritius. Right.
Yeah. They can't put it in can't predict it, and it's a very strange tides they have there. Sometimes it's a dangerous place to sail close to the island on the north part.
Anyway, I've got distracted us from talking about tides now, from whatever it was we were talking about before. Now I can't remember now what. Basically, QE being an idiot or something.
Yeah, what was it?
Well, the tides are a good subject. I like talking about that.
Coriolis.
Yeah.
Yeah.
I don't think there's any. Given that how they don't understand the difference between Coriolis and rotation, I don't think there's a chance in hell where ever. As I say, I think I'd have to spend 5 days, several hours a day with QE and Oakley to get through to the difference, because the Oakley keeps on saying he thinks that Coriolis is responsible for the 15 degrees per hour when it's got nothing to do with that. So these people, and I think QE got that from QE, and he also thinks that Coriolis is the cause of. That's right. He said that in the globe model, Coriolis is the cause of the rotation of the stars. That he says that's what we claim. So they completely confused the just normal rotation with the effects of Coriolis, because it's also rotationally. So they sort of conflated the two, and then they end up with this idea of saying, okay, can't have Coriolis, you got the stars rotate. Yes, I was like, definitely, that's right. He said the other day that the star rotation was caused by what we claim is Coriolis. We're never going to get through to these people, I don't think, unless I do as absolutely blue and I do an absolutely superb video. I'm going to do a 3D version of Coriolis one day to explain it as best I can, but it's still going to take 15 minutes or more, and I still think the chance of them understanding it are next to zero.
You can't educate someone unless they're willing to be educated.
Yeah, that's
I was just
another
going to
very
say,
good
Rumpus,
point.
do you think they're actually trying to understand?
Well, no, not well. I think they try to understand some bits of it. Some they do try. Obviously, they're what they want to do. Obviously, is to have it. They want to make it seem ridiculous. They want to not understand it, so they can say, "This is all bollocks, isn't it? Look at this. I don't understand this. Therefore, it's all bollocks, isn't it?" And of course, if they, as you say, Sean, there's nothing you can do about someone who doesn't want to learn. This is why they're worse than 7-year-olds. At least a 7-year-old in a school seems to be keen to learn normally, and you can get them to learn something. But if you don't want to learn, then that's the first step you've got to have. And if they don't want to do that, then you're stuck. Yeah, so I agree with that, Sean.
Yeah, but it's very simple actually. It has to do with the rotation, but it has also to do that the latitude circles away from the equator are getting smaller and smaller and smaller. So that's actually.
But it's not just that. This is another thing I must admit. Coriolis is a complicated subject. There are lots of globers who think that Coriolis only occurs if you go north-south, and you have a change in Bob the Science Guy's one, for instance, doesn't understand Coriolis properly, despite the fact he's made several videos about it. He thinks he's explained, and I've had this people quoting him saying that the east-west Coriolis, the Eötvös effect, is due to the change in the shape of the Earth. Oh no, it isn't. So I'm afraid there are lots of globers who don't understand that Coriolis does not just happen north to south. It also happens when you go east to west as well. And that involves basically getting back down to this, what I was saying earlier about vector cross products and understanding this and the Eötvös effect. And I think probably, even some very intelligent globers I know have discussed things, have made some basic mistakes with Coriolis. So it is a very, I think you need to have done something at degree level mathematics or physics to fully appreciate what's going on with it. So I think you need to be very careful if someone like Bob the Science Guy has made a number of errors about this. You can easily trip up and make some silly errors about it.
Well, I think definitionally it's very confusing because they don't tell it. There are many places that indicate Eötvös and Coriolis as separate topics.
Yes, correct.
Mark. But if in most lines of work we can actually. It's the same as the gravity application. If you use Einsteinian or if you use the Coriolis effect only from north to south, there's the most effect, and for most jobs that's enough. Of course, it also has from east to west, but do we need it because it's tiny?
The magnitude is similar depending on when you're at 45 degrees latitude. The effects are they're just in different directions. So, for instance, if you want to allow for bullets, if you're firing east to west on the equator, then the Coriolis force will cause an up and down Eötvös type effect only. But if you're firing north to south, then it causes possibly for you as a shipping thing. That most of the time the Coriolis force is an sort of east to west effect. If you're at the equatorial latitudes, as you get to 45 degrees, then in fact the going east to west will also cause it has a similar. You're almost worrying about the azimuth type thing, how it's affecting your horizontal effect, and that is going to be not at the equator. That's going to be not. You're not interested in the Eötvös effect, but the component going east to west will actually at the upper latitudes be. It's more. It's not. It does actually. The Eötvös effect is just the different direction of the Coriolis force. And when you're at the mid latitudes, then in fact that reaches the maximum effect, and going to east west is going to cause a similar effect to going north south. But
see, there you just
let me jump in.
You just used them as if they were separate topics.
Yeah, I know.
Let me jump in for 1 second. Shout out to Stevie B for 10 pounds. First, a small thank you, says Stevie. Oh, no, thank you, Stevie. I appreciate it, man. Really
Just to get back to Mork's point, they are the there's a thing called there's the Coriolis force, and it has two components that you can break. It has a vector direction, and then you can break that direction into a vertical component and in the horizontal plane component. And the one that's in the vertical component, so you've got the one force, and then you can break it up into two elements: the vertical component and the sort of horizontal component. That's the point that Mork's making, which is absolutely correct.
Yeah, right. Well, Coriolis force is a vector cross product. It's the cross product of the velocity vector of the object moving and the rotational vector of the Earth. Now, that resultant vector is perpendicular to both the other two, right?
Yep.
That's by definition. That's how a vector cross product works. Now you got to start looking at what happens when you start turning that thing around. That resultant vector goes from just purely east-west to just purely up and down. That's what happens.
Yeah, I mean, actually, if you're at the equator and you fire a bullet north to south, actually at the equator, the cross product is zero. So in fact, there is no actual Coriolis. Actually, people tell you they're talking about firing north-south from the equator, but in fact, until it starts to bend down, the trajectory of the whatever it is you're firing bends down, there is actually no. If it were to carry on at the angle it started off at, you would get no Coriolis force at all if you fired at the equator, firing north to south, because the axis. Go ahead.
But the ETVOS will be maximum there.
Yeah. Actually, wouldn't that be zero? Because you have to if you're firing north to south at the equator.
North to south, yeah, right.
Yeah, it's zero. But if you're firing east to west, then as you said, it's the maximum. But if you fire north to south, a bullet horizontally, the Coriolis force initially will be zero until it starts to drop down and the vector angle of the bullet starts to dip. Then it will have some thing. But if it can maintain its horizontal vector, then the cross product of the velocity vector with the rotational vector, which is omega, which is along the axis of the Earth, the cross product between two parallel vectors is zero. There is actually no force at all if you're firing horizontally at the equator north to south, which may surprise some people. It's quite a complicated subject. As I say, you really need to have done, maths or physics at a degree level to fully appreciate this, or studied it, obviously, in your own time. It's got a complicated subject, and it catches out lots of globers as well. And so it's obviously quite well beyond the understanding of a flatty who doesn't even understand what the difference between 99 and 100 psi is 1, or what 10 to the minus 17 is.
No. I understand that it also has the vertical, because that's why flat Earth thinks that the rockets actually end up in the sea, because they don't understand the Coriolis effect, why it's curving away.
I mean, one of the prerequisites for being able to understand this would probably be basic subtraction, not getting a bigger number when you subtract 2. That would help.
And I've just had a link. Eric, who's absolutely fantastic as a resource for information, has posted in the chat here a link to a book all about the Coriolis, and I suspect I could do with a good read of that. I haven't actually checked this in the chat, but he said he's posted it in the chat. He's got a fantastic resource of access to books and things. Eric does, and he's provided me with links. And I've no doubt this is a good book on how the Coriolis works. So if anybody who studies this, I suspect will then be qualified to discuss the subject.
Well, I happen to have another example of how thoroughly people can misunderstand Coriolis. Who's making all that racket? Sean.
Oh, it's probably me. I'm sorry.
Yeah. And before I do this, let me say shout out to Sofa King Sleepy for $5. Love your show, Big Blue. Rumpus is the only person who I can stand interrupting his own sentences and be what is that, knowledgeable at the same time. Yeah.
Well, thank you very much, Sofa. That's very, very kind of you. I was getting some flack from some other people in the chat about saying I was almost as bad as QE, so it's nice to get some approving comment.
I've got a video.
Maybe not.
I've got a video that Brian's Brian Leakey did the other day. And I don't want to beat up Brian. He's not here, but he did this, and I watched a little bit of it. And it's kind of interesting because he really totally misunderstands Coriolis. And I don't know, maybe we ought to watch some of that and see what we can learn about what these guys think.
Oh,
yeah,
nice.
There was a character on the show Green Acres. I'm sure people have watched it. Named Hank Kimball. Remember that guy? He reminds me of the way Rumpus talk. No offense, Rumpus, but it's just, yeah.
Yeah, I appreciate I do wind some people up. I'm sorry if I know I do talk over people sometimes. I do talk a lot, so I'm sorry about that. But just interesting for you, Blue, there's Gary Wabenga in the chat saying, I'm waiting for a Globee to show me a specific measurement for correction for Coriolis if of flying. And of course, we've just said earlier, I don't know whether you heard it half an hour ago, you don't need to. It's absolutely tiny. It's completely swamped by the slightest of breezes or wafts of air are much greater than any Coriolis correction you'd have to do in an airplane.
Well, Gary seems to think that we need a big meter up there on the panel in an airplane that says Coriolis to be able to correct for the effect of it.
Yeah,
Coriolis warning.
Yeah, warning, siren.
But back to what we said there is what I was saying earlier. They don't understand how an airplane's being flown. We're just trying to maintain a position over the desired ground track. That's all. That's all we're doing. And we don't really know.
There's a magic.
Yeah, from minute to minute, what the wind's going to do. They can't tell me that. I mean, I can. Go ahead.
And there's this magic box in these aircraft called an autopilot that's making corrections, or probably tens of corrections a second.
Yeah, absolutely. Hey, shout out to Digital Demonic Davros for $5 Australian. Well, now that was said, it's my turn. Rumpus doesn't know something. Shocker. Leaky was not bright on Jim's yesterday. Okay. I agree with you, Davros. I heard some of that too. Well, I'm going to swap mics around a little bit and get this where you guys can hear it, and then we'll...
Sorry to interrupt you, Blue, but Brian is actually trying... He created a little globe the other day, trying to... what was he trying to show? The parallel... the distance, the local sun. He actually made a globe, and he put some lines on it to the... I can't remember, I was showing great circles and things, and he was actually trying. I do believe that Brian is actually trying to learn.
I think he is too, and that's the reason why I say I don't want to beat on the guy. And the only reason I want to show this is just to illustrate how confused they get themselves.
Gary says you can't measure Coriolis. Well, of course you can, Gary. You need to, but only certain circumstances. If you want to worry about weather systems which take a long time to move from A to B, or you want to fire an artillery shell over 20 miles, then you do need to allow for Coriolis, and that's why battleships since World War I have had Coriolis allowances in their artillery shell, and modern guns, artillery pieces now. Any artillery piece firing over 5 miles or more has to allow for it, and they have software on board to correct for Coriolis. They need to know where you are and where you're firing to, and they make a Coriolis correction. If you want to land your shell within a few hundred meters of your target, you need to allow for Coriolis. Sorry, go ahead, please.
So let's see. I'm going to switch these mics. Hopefully I'm still working. Let me mute the... I'm going to mute myself in Discord, and we'll play a little bit of Brian's video.
It's roboting.
Yeah, it'll stop here in a second. So here we go.
So I'm going to show everybody, even if you beg the question with these anti-flat earthers, their definition of Coriolis force does not work on their model, and the devil's always in the details. So here it defines the Coriolis force and shows an object moving from the equator toward the North Pole deflects to the right. Okay, and now they show a diagram, and they show something moving from the equator north, deflecting to the right or clockwise. So their narrative is so far so good. So let's take a look at some examples
putting water in it
of this in real life and see how it holds up.
I tried scrubbing the bottom.
Okay, so they show a Foucault pendulum. It says it always rotates clockwise in the northern hemisphere. So yeah, so that follows the diagram so far, and the definition, so far so good. So clockwise in the northern hemisphere due to conservation of momentum. But then, oh, wait a minute. Now we're told that hurricanes are caused by Coriolis effect. But they go counterclockwise in the northern hemisphere. And I think they pretty much agree across the board with this. So the Foucault pendulum conserves momentum and goes clockwise, but the hurricanes conserve momentum and go counterclockwise. So which is it?
Well, it's both. Brian's having a problem here. He's not understanding that mechanism that causes the counterclockwise rotation of a low pressure system in the northern hemisphere. That low pressure is what's pulling, if you want to think of it that way. The high pressure is actually pushing air toward the low pressure center. And if it were not for Coriolis, it would just flow straight to the low pressure center, but it doesn't. It's being affected by Coriolis force, and that causes it to deflect to the right, and the only way it can get to the middle, which is what it's trying to do, is rotate the other direction. It has to rotate counterclockwise. But he's having a problem with that.
It's like two wheels that you put together, and
yeah,
one will turn the other way than the other.
Yeah, and that's.
What direction is the what the Foucault pendulum? Does the Foucault pendulum go clockwise in the northern hemisphere?
Yeah, it does.
Yeah,
it rotates to the right, but. Like I say, he's not understanding the mechanism of air masses moving toward a low pressure center. As they're moving, wanting to go to the low pressure center, Coriolis is saying, "Oh no, you don't. You're not just going to go straight toward that thing. I'm going to push you off to the right." And the only way it can get there, it's going to get there, it's going to go from high pressure to low pressure, is to rotate the opposite direction. So the net flow going into the low pressure center is going to be necessarily counterclockwise. It just works that way. Am I explaining it correctly or confusing the hell out of everybody?
Yes, I mean, I think you're making the key point that the direct, because remember, a Foucault pendulum, you set it off to swing in a plane which it preserves as the Earth rotates, whereas it's slightly different in the weather system. As Blue said, it's trying to flow from the high pressure to the low pressure, and then Coriolis causes it to go to a right angle to that direction, because as we talk about cross products, they're always perpendicular to the direction of the force, is always perpendicular to the direction of the flow.
Yeah.
And you're getting a bit of feedback here. Shall I switch off?
Yeah, that's coming from me. I'll play a little bit more, Brian.
So you dive in deep and you start really thinking about it, and you show them a cylinder, and they'll say that there is no Coriolis on a cylinder because the ground speed at the equator in the north is the same. So let's hear them.
This is true for a non-rotating sphere and a non-rotating cylinder. Once you're rotating both of them, Coriolis is effect only on the sphere, not on the cylinder.
Listen,
let me get to the point. I know exactly what your point is.
Bro, shut up. Can I fucking talk?
No, because I can't.
Yes, I'm going to mute him in a second. Hold on, I'm driving. But I am
please, dude, he won't even listen. How could he understand if he won't listen?
Mute Brian. He's the one that's not fucking listening.
Zanuck, relax.
If we took the Earth, okay, and we built up the ground from the equator toward the North Pole into a cylinder, then staying on the ground, okay, would be the same direction as if all that dirt that we just built up into a cylinder on half the sphere eroded away and followed the tangent. Now the projectile's in the air because all the dirt's gone on that cylinder. Okay, so he's saying if we built the dirt up, that there wouldn't be Coriolis because it'd be a cylinder. But now the dirt eroded away and the bullet's now in the air instead of on the ground. Now he's saying that there's still Coriolis. Now he's saying there's still Coriolis. First he's saying there wouldn't be on a cylinder, but going in the same direction as the cylinder, following that path, there would. So he's double speaking. I don't think he understands the question. Go ahead, Zenny.
And it's just what you were talking about, Rumpus.
Yeah, it said going in the same direction as the cylinder. Sorry, go ahead, please. Sorry, I think you stopped.
Yeah. Well, I mean, the surface of the cylinder is always lined up with the rotational axis of it.
Yeah.
That's the same thing as being on the equator, right?
Yeah. Correct. Absolutely
exactly
correct.
the same. So, Zanuck wasn't wrong. Zanuck was absolutely correct about what he was saying. You get that effect on a sphere because you're not running parallel with the rotational vector anymore. The minute you leave the equator, you're no longer parallel with the rotation vector, and a cross product appears.
You're very choppy, Blue. I don't know if you're.
Yeah.
Just me, but you're coming through. It's very choppy.
Blue is a bit roboting. Yeah.
Am I?
Yeah, very choppy.
I don't know.
But oddly, your the video you're playing isn't. So I don't quite understand that. Your video was perfect, but your microphone is choppy.
We switched mics.
Yeah, I can switch it back to just straight in the mic instead of the voice meter, and that fixes it. But if I leave it like this, you guys are going to get an echo when I play the video.
Okay, well I'll mute the stream or something, or mute you or something.
You have to mute this mic to play the video, correct?
Yeah, I got a whole bunch of buttons I got to push to make it work.
Yeah. Yeah, you need to write down a piece of paper for yourself, Blue. Next, when I'm playing a video, I have to do this and that and that. Yeah. Yeah, it's a right old pain, isn't it?
Yeah, but
it's
that's
like
part of
being
it.
on an anchoring job.
Yeah.
Discord cheat sheet.
So we're gaining a little insight into what confuses these guys.
It is a confusing topic. There's no doubt about it. I mean, Blue, you're obviously mathematically very capable, and obviously we've got Clive in the chat who's also been putting in the equations we've been talking about, the cross products and things, and the 2 omega, twice the omega time with a cross product with a velocity is the Coriolis force. But these working that out, and it's tricky stuff. So if someone doesn't understand Coriolis, or gets it wrong, I'm quite sympathetic. It's only by studying it quite hard do you actually get the right answers.
Well, yeah, it actually is pretty tricky, and for that reason, I try not to take them down the path of vector cross products, because I know they're not going to understand it.
Yeah,
all it does is just make it more confusing.
Yes, it's a tricky subject.
And to be honest, I only use the part of what I need.
Yeah?
Yeah, well, you're trying to do real stuff, aren't you,
yeah,
Captain?
Yeah.
Well, you don't have to know everything to know something.
Yes.
And that's
what you don't want to do is assume that because you understand a little bit about it, you understand everything about it, and start getting all Dunning-Krugery about it and saying this is how it's got to be. If you're stupid like bloody Q and don't understand what bloody 10 to the minus 17 is, that you're in no position to, you just don't show respect to the subject by then pontificating about it from a position of complete ignorance.
I think you and I have talked about this before, Rumpus. Every time I open up Wikipedia to Coriolis and I see that damn diagram of the merry-go-round or the spinning disc, it literally infuriates me, because I can't think of a worse way of explaining it. But on the other hand, if you're just trying to get the basic concept across, that's what you do, right?
Yep.
But it's a very, very, very elementary, almost absurd way of looking at it.
One thing, Blue, is that I saw that you were being quizzed and you were under a bit of pressure about some aspect where someone was saying, well, what, you need another reference frame. And you do, but the point is when you throw something, that then enters, that leaves the non-inertial reference. So if you're on a rotating thing, like the Earth, and then you fire a shell, or an artillery shell, you then have it, because I don't know if you've covered the bit earlier where he talks about needing a non-inertial reference frame. Perhaps I missed the start of your stream when he talks about that.
Yeah.
The artillery shell then enters a new reference frame. It leaves the non-inertial reference frame. So when QE was ranting, I think presumably at the start before I came in perhaps, that you need, where's this other inertial reference frame? The shell is in it. The moving object is in that inertial reference frame because it's no longer part of the it's not being held to the non-inertial reference frame of the rotating Earth. It then enters its own inertial reference frames. And when we say inertial reference frame, what we mean is that then the laws of Newton's laws of physics apply, and you don't have to allow for rotationy things. You just can use the normal force is equal to mass times acceleration. You don't have to allow for other what are called inertial forces like centrifugal, etc. So when you're in that inertial reference frame, like a shell is, there you've got your other inertial reference frame. And Blue is being hassled about this in some chat or something. I can't remember what it was now. But so there you do have the two reference frames that QE claims you don't have in that situation. You have the shell going along its own sweet way, not being affected by the Earth's rotation anymore once you've fired it, and then you have the rotating Earth. And so from the perspective of a rotating Earth, the shell is now in, assuming it's not being affected by the atmosphere. So obviously if it's being affected by the atmosphere, then it's effectively being reintegrated back into the rotating Earth. But let's for a moment assume there's no air friction and you fired a shell. Then it is in a perfectly inertial reference frame, and you are viewing it from a non-inertial reference frame, and therefore you have the two reference frames that you require for the Coriolis force to take place. So QE's claim, sorry, I think it was probably before I came in, where he claims, oh, well, so how can you have Coriolis then in an atmosphere that's rotating with the Earth? Where's the other inertial reference frame? It's in the thing that's moving. It's in its own inertial reference frame, is the answer. Finished.
It can be seen from that reference frame, but nothing ever leaves a reference frame or enters another one. It's always
okay,
in.
Right, okay. I better. Yes, I knew. I'm wondering if you're going to come into that. I have this. If you look at physics lectures, they talk about leaving and entering reference frames. Now, that does not mean you can't reference something from another reference frame. So, for instance, we can say, in the case of that artillery shell, we can still write equations for that shell from the rotating reference frame. But when we say something is in the same reference frame, we say something like, for people in a train, for instance, all sitting down in a train, they're not moving with respect to the origin of the train. So we can say all those objects, those people in the train that are sitting down, are all in the same reference frame. But if someone gets up and then starts running around, you can still describe in maths what that person is doing from the reference frame of the train. But normally in physics lectures, they say that's left the reference frame of the train. It's now got an additional, its origin is, it's now moving with respect to the other objects. It's moving with respect to the origin of the train. This is a bit contentious. I know Zach doesn't agree. I don't know if you're in this case, Blue. But I would, and physics lecturers certainly say, you've then left the reference frame of the train. You've now got a new reference frame. Although it's not, when you say we've left a reference frame, it does not mean to say that you can't describe mathematical equations to describe where it is. And that's the tricky bit. People say, oh, if it's left the reference frame, then somehow you can't refer to it mathematically. Oh, yes, you can. It just means you've no longer, in that set of things in that reference frame, you're no longer constant. You're offset from the origin of that reference frame is no constant anymore. If you're in the same reference frame as something else, so for instance, you've got a flock of birds not moving with respect to one another, they're all in the same reference frame. Immediately a bird decides to go and do something different, it's then left the reference frame of the other flock of birds, but you can still refer to it mathematically from that other reference frame of the birds, and it has then its own reference frame.
And
so you might not.
Right, and that's exactly where Coriolis appears.
Yeah.
It's an object that happens to be doing what it's doing, and from an inertial frame of reference, it would be traveling along a straight line. Yeah. But at the same time, we're not in that reference frame. We're on the spinning Earth. We're in the non-inertial reference frame. That's where we're seeing it from. And there, the path is not straight. It is curved. And the only way for Newton's laws of motion not to be broken is you've got to have a force to cause that. That object cannot curve like that unless there's a force present, right?
Absolutely right, Blue. And yes, I agree. Sometimes there's a little bit this leaving reference frames. I understand why you were sensitive to that, and other people, even Zanik, for instance, another chap who you were showing there. He initially objected to my saying I'd left the reference frame, and he's fought against me this. But if you see lectures and things, we talk. If you don't say something's left a reference frame, then it means that it means nothing. If I say to you that all the people sitting down in a train and not moving with it are in the same reference frame as a train, and then they get up and move around, are you then saying they're still in the same reference frame? Then it means nothing. To say something's in the same reference frame as something else then is meaningless, unless you mean that its origin is not changing with respect to the origin of that reference frame. So that's why we talk about leaving a reference frame. But what we do not mean is you cannot. It still means you can describe it mathematically, and you have to add in some extra equations, like Blue said, of the movement, some accountants for that movement. But physicists tend to think like, say, that's then left the reference frame, and you then have to put an extra accounting factor, a correction factor, for then to map it back into that reference frame. But that doesn't mean to say you can't reference it, but you have technically, as we call it, or I say we, many physics lecturers will say you've left the reference frame.
Yeah, and what they're really meaning is you have moved to a different point of view. You're now looking at it from a different reference frame.
Your coordinates in that reference frame have now changed. They are they are changing. They're not static.
Right.
Whereas all those people in the train, with regard to say the front of the train, and they're sitting down doing nothing, all the coordinates are remaining the same over time. But if someone gets up and moves around, then their coordinate with respect to the origin is now changing over time, and therefore we, as I'm saying, the royal we're then saying that you have left the reference frame.
No, come
Some
on.
people might regard that as contentious.
Come on, Rumpus, you get it in your head. There's no reference frame in nature. It's not something you enter and leave.
Yes, it is.
It's how. No, it's not.
Yes,
It's how you look at things. How you look at things, not where you look from, but how you look at things.
Well, in which case, then you never end the phrase "leaving a reference frame" should not be part of our English language. If you're always part of it, then you never enter or leave it.
It shouldn't be.
Well, I'm afraid physics lecturers would disagree with you. And
I'm afraid they should correct
no, they
their
shouldn't.
English.
Because if I say all the people in that train are in the same reference frame as the train, then I've communicated to you something very important, that you know that all those people sitting down are not moving with respect to the origin. And that's a very important thing it's a shorthand for saying that's what's happening. If they're all in the same reference frame, I don't have to spend ages saying no, their velocity with respect to the origin is not changing. I just say they're all in the same reference frame. And then you understand what that means.
They're looking from the viewpoint of this reference frame, and the projectile can do the same. It doesn't know it's inertial. It's not enter the inertial frame. It's inertial. However, it can keep and measure its own coordinates in the rotating reference.
If you have an artillery shell, let's suppose you had 20 artillery shells all doing the same thing. You would say, as a short-term way of reference, I could say to you, Chaiki, all those shells are in the same reference frame. And that immediately should tell you that there's no relative positional change over time. So it has a very useful phrase to have. Whereas if I said one of the shells is not in the same reference frame, you would then know that it's moving with respect to the other shells. And obviously each thing can have its own reference frame. You could decide where the origin of that reference frame is, but the relative coordinates of each one of those things is not changing of those 20 shells that I just talked about. And so the phrase being in the same reference frame is a very useful phrase to have, and it means that the coordinates of the things with respect to one another is not changing over time. So it's a useful phrase.
No, it's not, because
it is useful. If I say 20 shells,
Rampus, let me speak. We use reference frame to measure movement. What do you mean they don't move in relative to another? We don't need reference frame for this, right?
You do.
We can just measure distances.
No, if I say they're all in the same reference, I say the 20 shells, or those people in a train, are all in the same reference frame, you know that they're not moving with respect to one another.
No.
Now, if you decide the reference frame
at all. No, because I can have them moving in the same reference frame.
No, then they're not in the same reference frame then.
Well, they can say they are not in the same reference frame. For me, they are.
But that's not useful. Then the phrase being in the same reference frame has absolutely no use that phrase would be redundant in the way you're using it. It would make
No, it's not.
no use. There's no use of.
No,
What's
it's
the
not.
point of saying something's in the same reference frame if things can move around with
Because
respect
that's
to one
how I
another?
measure. I have a reference frame, and I measure distances and time in that reference frame.
Yes, but then you don't say they're in the same reference frame. You can do that to any object. In other words, every object is in one reference frame. You could say, I could pick on a reference frame, and all the objects in the universe are therefore in that same reference frame, and they can never leave it. So it's not a useful. It's not a useful phrase to then say they're in the same reference frame. I mean, you can say from what you're saying that from the origin I'm picking all these objects in the universe of this, but that doesn't mean to say they're in the same reference frame. You're using the same origin, and then you can have mathematical equations for all the molecules and suns and galaxies in the universe, but they're not all in the same reference frame, although you're referencing them from that origin.
I can map them in this reference frame. I can measure their movement in this
I didn't say you
reference frame.
couldn't.
Then they are all in this reference
No,
frame.
they're not. No, that's the difference.
They're
That's why
always
you can use the
in the
phrase.
same-
That's why you can use the phrase. I can measure everything from a reference frame, so I can measure all the stars,
That's what
molecules.
reference frame is.
No, it's not. It means
Yes.
more than that. To say something's in the same reference frame just means that you can measure, and then no one's disputing that. You can, as I say, you can have one origin and then say, I now wish to measure all the molecules in the far distant universe with respect to that. But they're not in the same reference frame. They're just being referenced from that particular origin.
Yeah, that's a reference frame.
No, it's not. Yes, okay, it's a reference frame in the origin, but they're not in the same reference frame. You're referencing objects using that reference frame. So but from what you're saying, then everything is always in the same reference frame, and the phrase that's redundant. But it's effectively what you're saying.
Always in the
You're saying I've got a reference frame, and therefore everything is in the same reference.
You can choose any reference frame. you want.
Both. Stop for a moment. Everything is always in all reference frames. You can only look from a different reference frame. At C, we use 4 different reference frames, and you're both right, and you're arguing over the same point. The only thing you have is everything is always in all reference frames. It's the thing you're looking from one of the reference frames, and that's how you see it.
I mean, what you're using it, Chai, because you're effectively saying, let's suppose we decide to take the origin as the centre of the Earth, and then I want to map out all the objects in the universe. And then I decide to have another reference frame based around the origin of the Sun, and I did the same thing. And then you presumably are saying, all the objects, those are, you would say that all these objects in this one reference frame, and the other one, and then in another case for the Sun, you've got the Sun reference frame and you've got the Earth reference frame. But all the objects are in those reference frames. So it's redundant to then say these objects are all in the same reference frame. Unless you want to say, well, there's another conditional comment. Yes, you could say, okay, the coordinate I've got for this star from the Earth reference frame, and then the coordinate I've got from the Sun origin is from a different reference. We have a different value, and so you would not want to confuse if you wanted to put the coordinates of that star in one reference. You wouldn't want to mix up your coordinates in the 2 reference frames. And then you could say, well, those are in 2 different reference frames. So I think that's the way that Chike's trying to use it. But lecturers, there's 2 levels to this, perhaps. And then there's the time when you say all these objects that are doing the same thing with one another. So, for instance, we talk about the Earths on the rotated surface of the Earth. They're all in the same reference frame. And that means that they're not moving with respect to one another. So perhaps there are 2 ways of being in the same reference frame, and you're just using one of them.
No, look, Wikipedia says, in physics and astronomy, frame of reference or reference frame is an abstract coordinate system. That's it. That's it. You don't leave it. You don't enter it.
Then how come that physics lecturers talking about entering and leaving reference frames?
Huh?
Then how come physics lecturers, when they're giving lectures to university students, they talk about
them.
Well, I do know why they're talking about it. I've just explained why. And when you're in a train of people and you're sitting down, you're in the reference frame of the train, and when you get up, you're no longer in that reference frame, although you can still have a coordinate with respect to the origin of the train. It's
so if I'm going up
the
train, I'm no longer in the reference frame of the train, right?
You're no longer in that reference frame. You have to have a correction. So you can still be referenced from
I need to have a correction.
But
Why?
you're not
measure my coordinates
because you're now moving with respect to the origin.
Good. Can I
you
measure
on a different reference
Can
frame.
I measure my coordinates in that
Yes,
train?
you can. I keep on saying this. I've said for the 10th time now. You
So
can
I'm there.
measure the coordinates in that reference frame. I said that all along. It's one of the first things I said, that just because you could measure the coordinates of that person in the train reference frame does not determine whether or not it's in, we're talk about leaving the reference frame or not. That person's walking around, has left the reference frame of the other people on the train, although you can still describe a coordinate to it from the origin of the train.
So first of all, none of the people have the same reference frame. Why? Because the origin, they're on a reference frame, right? So none of them is in the same reference frame.
They are. They've
the
got
train, because you need to choose a point of origin.
Their coordinate, their relative coordinates are not changing. Therefore, they're in the same reference.
So what? But the origin is different.
What do you mean? So what? That's an important thing to understand.
Look,
It means it's very important to tell you.
I see you 1 meter behind me. You see me 1 meter in front of you. It's not the same frame of reference, is it?
Yes, it can be. You can have a shared coordinate. You are not moving with respect to one another.
So if we have a shared coordinate, we can measure moving object in that coordinate.
But it's not useful then to say, if I tell you you're in the same frame of reference, then you know, well, most of the time in the context, that you are not moving with respect to the other person. That's a useful thing to understand with a quick sentence. So if I tell you all the people in the train, bar one, are in the same reference frame, you know that they're not moving. I mean, obviously, you're just using perhaps the reference frame as in the second form that I described. But physics lecturers, when they're describing things, often say this is in the same frame of reference, meaning that they're not changing their relative position in a coordinate system. So the origin of this people could be any one of those people could be the origin, or the train could be the origin, and the coordinates of those people will not be changing over time, and therefore we say, all those people are in the same frame of reference. And when you get up and leave it, you'll know you are now moving with respect to the origin, although you can still describe it mathematically perfectly happily. We say you're no longer in that same frame of reference as the people.
Like I said, I can say that all the people are in different frame of reference and they are all moving in the same direction.
But that's not useful.
But it's very useful.
It's not useful because I can say if all those people in the same reference frame, you know that their coordinates are not changing over time, and I can say I can forget that. But I now fully understand that all those people are not moving, and I've only got one mover. You can't describe that using your language. You can't make the.
Yes, I can.
You can't. Well, you have to do it in a much longer way. You have to say all the people in the train are not moving with respect to some origin I'm going to pick on.
Right.
That's a much longer sentence than to say they're all in the same frame of reference.
Yeah, and then you create confusion, and people say, you need to frame of reference. No, you don't need to frame of reference.
Again, everybody is in all reference of reference. Rumpus, you can look from a different frame of reference, but you're still in the same all frames of reference. Shaik, it depends on what the person imagines.
I think I've made my point. It seems to me that there's a useful phrase to say it in the same frame of reference, and it can mean more than just using the same, some origin that you know to respect to. Physics lecturers do this. They say say for instance, all the objects on the surface of the Earth are in the same frame of reference. They're not moving with respect to one another, and yet, and if you had something moving on it. Anyway, I think I've made my point, and I understand it's.
Of course,
it's a little bit contentious.
Aren't we spinning? Aren't we spinning? Of course, we're moving in a respect to one to each other.
Yeah, but all the objects on the surface of the Earth are moving in the same frame of reference. An object, for instance, an artillery shell, is no longer in the same frame of reference as the objects on the surface of the Earth, and that's why they're in a different frame of reference. And you know by the fact that I say this is in one frame of reference and this is another one, that you know that it's moving with respect to the origin of the coordinates. Whereas the other set of things, the rotating objects on the Earth that are stationary to the surface of the Earth, are in the same frame of reference and not moving with respect to the coordinate. So by telling you they're in the same frame of reference, you immediately pick up that's what I mean. Whereas with what you're saying, you don't have to say, well, all the objects on the surface of the Earth are not changing their coordinate system with respect to an origin, which is much longer and just not useful. Too.
Well, it is useful, and that's when they talk about relativity, they always talk about never mind how many objects there are. Every object is in its own frame of reference. Every object.
No, it's
so
not.
Yes, and then the frame of reference moves.
Not necessarily.
Yes,
not necessarily. You just made that up. You can have things in the same reference frame. They can have, but you can just pick on one reference frame and say all these objects are in this same reference frame.
You can say everyone is in its own.
I mean, if you do kinematics problems and things, you often say group all these objects together, and you know they're all behaving in the same way, and then you can say all these objects in the same frame of reference. I can then treat them, move them all, and have the same equation, and then it's only the relative coordinates they've got that then determine how, if you want to know the particulars of any particular object. But you've got a group property, and you say all these objects in the same frame of reference, and then you can just treat them all as one object and then work out the details later on. And whereas with your thing, if you start worrying about all having an individual frame of reference, you're just complicating the issue enormously. Anyway, I think that's probably enough on that subject. I'll do a video on it or something, and I'll go and get some physics lecturers to explain to you what we mean by being in the same frame of reference or something. It is slightly awkward, and because you've got to decide upon having the same origin of a frame of reference, and then saying, I'm going to now. You could argue, so say, if you want a frame of reference of all the objects in the world, in the universe, reference to the Earth or to the Sun, those are definitely in two objects, although the same objects, they are in two different reference frames. But anyway, I think that's probably enough on that subject. We'll bore everybody stupid.
That's been a lively discussion. You want to listen
reference frames is always contentious.
Yeah, you want to listen to a little bit more of what Brian says?
Yeah, go ahead.
We could listen to that. Yeah, let me push all these buttons again. Hang on.
There are consequences to the claims these people make that they never think through. The devil's always in the details. So when they claim that the atmosphere moves with the Earth in lockstep, basically, that means it has to start moving faster the higher it gets. And they stick to that story. So let's think about what I said in that video, and let's picture globe Earth and cylinder Earth side by side. And let's picture there's a metal rod in the middle at the center of rotation. Now, they claim there's no Coriolis on cylinder Earth because you're equidistant from that rod from the equator all the way to the north. This is why I used the demonstration of building up globe Earth from the equator to the North Pole into cylinder Earth to show them how their own story unfolds. Okay, so picture we're standing on cylinder Earth on the equator facing the North Pole, and we have an artillery shell 5 foot off the ground. We fire it parallel with the ground, and it makes it 20 miles before it hits the ground. Okay, they agree there would be no Coriolis because the ground speed doesn't change on cylinder Earth. Now picture we're on globe Earth at the equator facing the North Pole, and we fire a projectile 5 foot off the ground. We fire it out parallel, so it's in a tangent. So it starts off following the cylinder. So think with me for a second. I used this example to try and explain it, okay? I built up the Earth, the globe Earth, with dirt and fired the artillery shell parallel with the ground. But right when I fire it, all the dirt erodes, but it still takes that path until it drops underneath that tangent line from the equator to the North Pole or towards it. There's going to be no Coriolis. In fact, if I fire it at an upwards angle, there's going to be reverse Coriolis. So this is how you know their firing tables are full of shit, because if you fire out at 0 degrees until it drops down underneath that tangent line, which might not be long at all, but there's going to be no Coriolis. But let's say we fire up an artillery shell at any angle at all, there's going to be reverse Coriolis. So instead of deflecting to the right, it's going to deflect toward the left because we're entering an area of even higher rotational speed, not lower.
Well, hang on. Anybody got any ideas about that?
Well, I think I know what it gets with the firing up, but who fires up?
Yeah.
higher from ground to ground. And if it's mountains, usually you're on the mountain too. You're not going to get much change in elevation.
I sort of get part of his point. I understand that if you, what he's talking about is converting the Earth into a cylinder, a rotating cylinder. And as we talked about to start with, if you're causing your projectile to move parallel to that surface, you're still lined up with the rotational axis of the cylinder. And he's right, there is no Coriolis. But then he introduced a funny concept that somehow this mound of dirt that he's piled up on top of the Earth to turn it into a cylinder flies away or whatever, and the bullet now takes a different trajectory, and it's no longer moving parallel to the axis of rotation. Okay, Coriolis appears. Absolutely it does. Now, how does he get from that to reverse Coriolis? Anybody?
He means that if you fire a shell up, straight up, then the higher it goes, the slower is its tangential speed, right?
Yeah.
So it's like reverse Coriolis in the other direction, I think.
I suppose that's what he's talking about. I'm not totally sure.
Oh, you guys forgot beating Pete. You have an upwards acceleration or not?
The drop towers actually do show that. When you go into the drop tower in Germany, you'll see that. So I mean, I don't know what his problem with it is.
I think the best way to describe it on this cylinder, that if the cylinder, let's say, has mountains and valleys on it, if you fire from the equator, let's say sea level, to a mountain, then it will be a reverse Coriolis. It will be to the other direction. And if you fire to the cylinder, there will be no Coriolis, and below the cylinder there will be Coriolis, as we know. I think.
Yeah, let me give a shout out to Davros again, another Australian $5. You don't leave, you change reference frames. Do you know the difference? I agree with you, Davros. We don't leave, but we can change if we wish. We don't have to. We can observe anything from any reference frame. But yeah, you're talking about dropping things. Absolutely. If you take an item up on top of a tower, tall tower, drop it, it will land in front of the position you dropped it from. It'll land to the east, won't it? Why? Because it was
the
moving.
plumb bob from from a tower like that. The plumb bob will if where the plumb bob is working, right?
Huh?
You're breaking up, Mark.
Oh, okay, forget it. I'm shitty coverage down here.
You're back now, I think.
Okay, I was just
no, you're broken up.
in tower or whatever they call it. Fuck it.
No, you broke up totally there.
Yeah, that's a little different situation. Reverse Coriolis, huh? I got to think about that.
Well, I'll make a drawing.
If you're going to change a reference frame, you must be in a different one to the one you were in before. Therefore, you've left the original reference frame. Or you can say you've changed which is the reference frame you're referring to something from. But
it's only viewing from different reference frames. You're still in the same reference frame.
It's all very. I mean, it is a bit of a personal set, but I think, yeah. Yeah. Anyway.
Shout out to Stevie B at £5. Says from my reference frame to yours, I think. With any luck, you're right, Stevie. With any luck, we'll see. YouTube seems to think so.
Oh, sorry. To Rampus, on board of a ship, we think 4 reference frames. It's relative to the water, the relative movement. The ship is going to, the other one is going towards you. The relative motion through the water, the true motion, the other ship is coming towards you. Relative to the Earth, the ship is relative coming towards you, and the relative to the Earth, the ship is truly coming towards you. So I'm quite used to think in 4 different reference frames at the same time.
That's fine, yeah. I mean, there's no limit on describing on the number of reference frames you can have, and you can describe everything from any number. You can have the reference frame as being an atom of oxygen or something if you want, and everything else be jiggling like crazy. Yes, I'm not suggesting there's any limit to the reference frames you can pick on or the arbitrariness of them, but I was just describing you can group things together by saying they're in this same reference frame. Now, whether or not you say there's 2 ways you could say that's the reference. Are they moving with respect to one another, or the coordinate, or the origin, or are you saying that all these objects I'm using with regard to say this reference frame, let's say, as I say, with Earth, or these same objects or the other objects from another origin point? So you could then say, these objects are being referenced from 2 different reference frames, the same objects, and therefore you could say they haven't left them or something. I'm just looking at them from 2 different perspectives. So, there's possibly some ambiguity about there's an equivocation here about what you mean by them being in the same reference frame. Because I mean, then see, it doesn't really make it's not a very useful phrase to use to say it's in the same reference frame at that point, saying you've got the same objects. So to use the phrase, and Chaika was basically saying you should abandon the phrase in the same reference frame. Well, I'm afraid that is a phrase that's used, and if you do use that phrase, then I'm afraid you can then leave it and have things that come in and out of that particular.
Correctly said is looking from the same reference frame, because everything is in all reference frames at the same time. You only can view it from a different reference frame.
Yeah, I mean, it all depends whether you regard as you can still view everything from every reference frame. You can view all objects from all reference frames. The question is whether or not that constitutes being in the reference frame is whether you can view it from a reference frame. That's really what it comes down to. So I'm not disputing you can review anything from any reference frame. I'm just saying that when something's in the same reference frame, that means there's a bit more to it. The objects you happen to be looking at they've got their own consistent reference frame, like people on a train that are not moving. They've got the same reference frame as the train. Although obviously you can decide where the origin is, and you could, if you wanted to, just say I'm going to pick this person in the middle of the train, and then obviously all the other people not moving with respect. Then we just like to group things together and say, right, all these people in the same reference frame, and so I only need to write one equation for all those people, and then if I've got someone moving around, I then need to write a special equation for this other person who's moving around. So I only need 2 equations. Whereas if I then say I need to have every equation for every person in there, and it's just not. It's just convenient to then group things together and know they've got similar properties. But anyway,
then you get the calculation from the view of the moving train, or the view of one person in a train, or the view from one person outside of the train that sees the train moving. But it's a view. They're all in the same reference.
That's right. There's no limit on the number of reference frames. There's no limit on the origins you can pick. There's an infinite number.
Yeah.
Right.
But they're still in all reference frames. It's only the
they
view
can reference
from
any object from any reference frame can be referenced. Yes, that's not. But that's not. When I say leave a reference frame, it does not mean that you can't reference another object. So this is where the confusion lies. This is why I think Blue and others might not care for it. Is that the idea of leaving a reference frame means, hold on, that means you're telling me I can't write an equation that describes this object from this origin, this reference frame? I don't think so. And then indeed, that's not what I'm saying. It's a really definition about viewing and in, I suppose, is really what it comes down to.
Yeah,
anyway, I think. Oh god, we're going to kill anybody. I don't want to bore Blue and everybody else. It's silly. How many hours have I spent on this?
Really?
Unless
We'll
we're
listen to
happy
it.
to talk about this for indefinitely.
Yeah, we'll
Well-
listen, I guess, to a little more of Brian, maybe.
Wait, Blue.
Huh?
I posted the drawing. You said if you shoot from some point, let's say at the equator, to that mountain that is above the cylinder, above the line that makes the cylinder, then you'll get reverse Coriolis in the other direction. If the object is below it, you get the Coriolis. Depends how high it is.
Say it again, Chai. Can we see your Can you share the diagram, Blue, so we can all see?
It's in the chat.
Yeah, I know, but other people, we're talking about it. Should be Blue should be sharing, shouldn't he?
Yeah, I've got to do a bunch of stuff to show anything from the chat.
Okay, all right.
Unfortunately, shout out John Rapp for Australian $2. I dare you say reference frame 137 more times.
Sorry, John.
Yes, sorry, John.
Perhaps Blue will have a reference frame special or something.
Oh God.
And then we can and then Chuck can bring along his diagrams, and I'll bring along mine, and goodness knows what.
Oh hell, let's listen to Brian go on a little bit more about this, and then we'll call it off.
So we know that if we follow the cylinder, the surface of the cylinder, we know that at that angle that it's equal. The speed is equal. So you don't even have to do the math. The surface of the cylinder is going to remain at an equal rotational speed. So on a sphere, it doesn't matter what we're on. If we maintain that angle is the surface of the cylinder, it's going to be the same rotational speed. So let's put all this in perspective. If we are on the ground at the equator firing north, and we fire in a tangent, as long as that bullet doesn't drop below that tangent, we know that it's staying equidistant from the metal rod. So it's entering an area the same rotational speed as it left, so no Coriolis. We know that if we fire out further and the bullet drops below the tangent line, we know that the bullet's entering an area of lesser rotational speed, so we'll get deflection to the right. Now we know that if we fire at an angle above that tangent, above the cylinder shape tangent we've discussed, we know that it's entering a region of faster rotational speed, so it's going to have reverse Coriolis, for lack of better words. It's entering an area of faster rotational speed than it left, so it's going to deflect to the left. So a real life example here. A sniper's laying on the ground, his muzzle is 6 inches off the ground at the equator, and he's shooting north, and his target is 6 foot above the ground. Now we know that if his target's 2 miles away and 6 foot above the ground, then we know that that bullet is entering into an area of a faster rotational speed than it left from. So the firing table will be exactly opposite. It'll be dead wrong. If his target is 2 miles away and it's the 32 inches, that's earth drop from that distance, and plus the 6 inches, if the target's that high, there'll be zero Coriolis. It'll level out. So the bullet would be entering area that's equidistant from that metal rod, therefore the same rotational speed. So anything lower than the tangent, Coriolis, deflection to the right. Anything level, anything on a tangent that maintains that line will level out and there'll be zero Coriolis. And anything at a higher angle, anything at an angle steeper than the tangent line is going to be reverse Coriolis. So we've broke the globe today, pretty much, and we learned that their claim on its face that things are conserving momentum. The Foucault pendulum spins clockwise, but then the hurricane spins counterclockwise. So for them to try and maintain this delusion is unacceptable. It's not honest. But I'm going to try and get this out there. But this needs to be discussed. And then they tried to look at right here where
I figured out why Brian sounds so tired all the time. The mental gymnastics he goes through to try and figure stuff out is exhausting him.
Yeah.
Yeah, it's a struggle for him.
The problem is he's not doing the calculations. He's not actually finding out how much the change in velocity is going to be for going up 6 feet. It's going to be fuck all. How much did that increase the radius of Earth?
No, the thing is that it will not drop, right? It will not drop from the horizontal. And it says in this case you shouldn't correct for Coriolis.
But the worst part is he explains the globe, and his conclusion is it's not a globe.
Yeah. That's
so they've actually got this all wrong. Like, I mean, Coriolis is just an effect. It doesn't make the Earth a sphere or not make it a sphere. It's got nothing to do with it. Gravity is what makes the Earth a sphere. It crushes everything into a sphere, and so whether it's rotating or not, it's got nothing to do with the fact it's a sphere, because you could have a spherical planet that's not rotating and it's still a spherical planet at the end of the day. And Coriolis is just an effect that comes about because you're moving on a rotating sphere. But whether there's Coriolis or not, or whether it makes sense, doesn't actually change the fact that we're living on a sphere.
Right, but if he could show that Coriolis was not behaving in the way that we think is necessary for a rotating sphere, then he would have a way of invalidating a sphere.
Well, that's what he thinks, does.
Yes, but so in other words, if you could demonstrate we're not getting Coriolis effects on the Earth, which we know to be rotating, then you would invalidate something in the regard the spherical Earth model. But so we do have to see these Coriolis effects to validate the Earth, and if you could show they don't exist, then you could say that the globe Earth model is incorrect.
Yes, that's sort of from their point of view, isn't it? But there are other ways to confirm that. You don't have to take Coriolis to see that the Earth is spinning. There's much better ways of measuring it to much higher levels of precision. And they're just picking on one. They're nitpicking, in my opinion.
Right, but if they could demonstrate there were no Coriolis effects, then we would have a big problem.
If there was not a Coriolis effect, then they can say or it's not a sphere or it's not spinning, but because the Coriolis effect needs a spinning sphere, but still, if it was a sphere but not spinning, you wouldn't have Coriolis. If it was flat but still spinning, you wouldn't have Coriolis. You need both a spinning sphere to have Coriolis.
Well, you can have Coriolis effects on a flat spinning disk, but they would be different. It wouldn't change. For instance, we obviously know that if the disk was spinning, then and you fired something on that, then the Coriolis different. So it wouldn't be the same sort of Coriolis anyway on a spinning disk as opposed to a spinning sphere.
Sorry, that's what I meant. You still have Coriolis on a spinning disk, but it's different.
Yeah. So I mean, I understand that Rob's making the point that there are many better ways of working on rotation, but they're just trying to tackle one of. They could say, well, I'm just going to focus on this thing, this necessary consequence of being on a rotating Earth. Oh, and it's not there, therefore that invalidates the there and then. I mean, you only need one valid way of invalidating a rotating Earth, and you've either then end up with a logical incompatibility. It suggests your physical measure. One of the things you're measuring in the real world is not correct, so you've got a paradox then. And of course, we know there's no paradox. But if he could show there was a paradox, and then he could then say, well, now I'm going to go on to measuring the other ways we claim, like for instance, the stars rotate, and he could say, well, actually, these stars are rotating and we're not. And he could then, you know, there are all sorts of ways, and they could then start tackling each one of the other things that show that. And things like as we were talking about, the dropping of the object from that Bremen tower, obviously also demonstrates Coriolis, and that the things move to the east from where you are, and you can demonstrate that with a rotating thing. Though obviously you could have, on a flat Earth, presumably, again, at the rotating disk, you would get a similar effect, but obviously it wouldn't be latitude depend. It'd be the dependence on the latitude would be different on a disk than it would be on a sphere. And obviously, I mean, you get lots of people saying, "Oh, you can't use the Foucault pendulum as proof of the Earth's rotation because no one's ever taken the same equipment from one place to another. They've always done it independently." Well, I mean, that's bollocks. You don't need lots of people. We verify science, but don't have to be in the same place. Although obviously this one's supposed to be location specific. I don't think anybody regards it as necessary to take the same equipment from one place to another. If you can duplicate the equipment sufficiently well, then and you get the result, and if all the results are consistent, they all agree with where they are, then you don't need to go to the palaver of moving all your incredibly long pendulum from Paris to New Zealand or something to do the check. If everything everywhere agrees that the answer, then you think it's rather redundant to do that.
But also, on my last trip, I had to be very quickly with my celestial navigation close to the equator, because the sunset and the nautical twilight is very short there.
Oh yeah.
Yeah, it has something to do with the Earth is a globe or something.
I got your sketch up on the screen now, Shaki.
Yeah, well, it's simple. If you fire onto something that is above the tangent, then the Coriolis will be to the other side, to the west. If you fire from to the north, let's say from the equator to the north.
Or is this a side view? We're looking
Side
at the side
view,
of the Earth.
of course.
Okay, just checking.
Yeah, we're looking on the Earth from the side. You're on the equator. You're firing north. If you fire to something that is above the tangent, the horizontal.
You said you're firing on the equator. That's firing
from the equator to the north.
So it is a plan view. You said it wasn't.
Well, it's
where's the pole on this, Chike?
The pole goes from top to bottom, where the arrow goes.
So you're not firing from the equator, then? You're firing from the top.
Yes, the equator.
You just said that north to south. Hold on.
No. The equator goes from that point down.
I've totally lost you now. Where's the axis of rotation?
Oh God, give me a second. I'll draw the equator.
And the axis, please.
Really, you need the axis?
Well,
Are we looking into the axis right now? No. That can't be right. I'm seeing it wrong.
Well, he said he was firing from the equator, so I'm assuming this must be a plan view.
Just draw a 3D shape.
That's the equator. See it now?
The red line is the equator. Oh, I see. Right. So the axis is left to right. So the axis of the Earth is left to right.
Okay.
Yes. So if you fire above the horizontal, the deflection would be to the west, not to the east. You fire below the horizontal, then the deflection will be as we expect to the east. So in the case of 2 miles and 6 feet, he's right.
Can you say that again? If you fire above or below, it's going to make a difference to where the deflection is.
Mm-hmm.
Not if it's at the same angle.
This is a cylinder. Imagine it's a cylinder.
Hold on. Where's this? Where?
Well, you don't see the cylinder. You see just the. Imagine I cut the cylinder. All you see is the top of the cylinder.
You told me just earlier, well, you agreed, I think, that the axis of the Earth is left to right across this image, isn't it?
Mm-hmm.
But now it forms a cylinder. The trajectory he's making forms a cylinder.
No, the horizontal forms a cylinder. The horizontal on the equator forms a cylinder, right? Like Brian did it. From the equator north. If you fire above this cylinder, the deflection will be to the left because the rotation up there is faster than yours.
No, if you had the same height above or below the horizontal, I think you would get the same deflection.
No,
How?
I understand. The airspeed will be the same, only the ground speed.
The ground speed. The top of the mountain speed is greater of the tangential speed of the top of the mountain is greater than the surface at the equator. Because it's above it.
Then you will have a very, very, very high mountain.
Well, in the case of 6 feet, it's enough. It's already above.
So let me get this right. You're saying that arrow is representing the angle you're firing your thing, and if you're saying if this arrow was the same angle below that brown line, you think it would change the direction of the deflection?
The brown line is probably referencing
I think that's wrong. Because it's the cross product of the vector direct velocity with the axis, which is effectively the same as that brown line, and that would give you the same. That would give you the same direction.
What would be the tangential velocity of the top of the mountain? Is it greater, the same, or less than the equator?
Well, it's obviously greater, obviously.
Greater. So the bullet will deflect to the left. West.
That's it. Brian has debunked the globe.
No, he didn't. But he was right on what he said. It doesn't debunk anything.
Nope, it's debunked.
He gets 2 points for being correct.
Yeah, I think scale fools us a lot here.
Yeah.
No, he was talking about the 6 feet, and the 6 feet in 2 miles is indeed above the tangent, right? We have a drop of 2 feet. We have about 2 feet drop there, and the object is 6 feet, so it's above, and the deflection should be to the other side.
Yeah, this is something that could potentially be true in a very special case.
Yeah, if you have a very large mountain close by you, and but
yeah,
no,
that may be true. You're not going to go very far before that. Before you're always below that tangent line you've drawn, always.
It's when you're trying to shoot people on Mount Everest.
Yeah.
Usually
on the bottom of Mount Everest, and
soldiers usually do not stand upright when they're being shot at. They usually dig down.
And of course, the other thing too is it's all going to be dwarfed by the 100-kilometre-an-hour winds.
Yeah.
All these effects are going to be tiny in comparison.
And back to something Rob said earlier that I wanted to touch on, and that is actually the simple fact that it's the wrong question to be asking. If the Earth is rotating, Coriolis is present. It can't not be. It has to be. The question is not whether there's Coriolis force or not. The question is whether or not the Earth's rotating. If it is, forget about Coriolis. It's there. That's not optional.
Yeah, and in my game, Earth rotation is a big part of what we do. You know, the science project I'm involved in, our gyros will not work on a non-rotating Earth. Simple. End of story.
Oh yeah.
To heads in the chat, the North Pole is on the left. Is at the left margin there of that circle. The left limb, if you will.
Yeah, 9 o'clock and 3 o'clock.
Yeah, right, right. And the red line, brown line, whatever color that is
12 o'clock.
Yeah.
What I didn't understand is the hurricanes, exactly how they form to rotate left. I have some image I found. Hold on.
Oh, good.
Shaki, I'm planning to do a video on that, why merchant vessels use Coriolis to actually avoid those hurricanes. And that has to do with it. But it's not all of Rambus, there's not all Coriolis in it, only that part.
Alright, say it again, sorry.
No, I said I'm planning to do a video about merchant ships using Coriolis in their work, and the thing we do is actually plan routes and take hurricanes and tropical storms in account and how to avoid them, and we use Coriolis to predict where the storm is going and how we can avoid them.
Ah, right. Okay, so you don't use it to decide in ship navigation. You're just simply working out what the weather systems will do.
Yeah.
So I thought earlier you were implying you actually had a Coriolis effect on your boat, like a sort of projectile. I didn't quite understand what you were saying.
No,
right.
We use it in a different way.
Ah, right. So you're just using it on weather systems. Great. Okay. Oh, it's very interesting. Okay.
Yeah.
I think
we still use it.
Yeah, atmospheric modeling must take Coriolis into effect. It must be one of the parameters in an atmospheric model.
Absolutely.
I think a good way to demonstrate it would be to put two treadmills side by side, run one at a half a mile an hour, run the other one at 1 mile an hour, put a foot on each and see if you turn.
Interesting.
A good one. Yeah.
Mm-hmm.
Just like the thing I did with the two cameras spinning to prove the two rotations of two rotation points of the stars. I took two phones together, one camera up and one camera down. Turned them hanged them on wires, turned them, and let them go. And halfway, I turned them around and did it again to make sure that I actually didn't cheat. One of my videos.
I think the example that Chike gave is an example that also is another confusing thing about Coriolis. That when we talk about something when you're firing north-south and it's missing an object that you're looking at north-south, I think I'm correct. I'm not absolutely sure about this, but when we say you've got a Coriolis force, the reference frame, going back to reference frame here, is of where your object is. So although you might say I'm looking something directly north of me, I'm not sure it's correct to say, as Chike was trying to give an example with the mountain, whether that's correct to use that as a reference frame of saying I've missed the mountain by going further. It's the Coriolis force is affecting from the reference frame at the origin of your motion.
Yeah.
And so I don't think, and this is where people, I need to think about this a little bit more, but I think there's another factor in that people call Coriolis, like firing north to south and missing a target. That might not actually be Coriolis. That might just be the difference in the rotational speeds. And you're thinking in terms of the target, saying, oh, look, there's the target that's directly north of me. And I'm not sure that's in the same...
That's not Coriolis?
Oh, yeah.
That's all. Yeah, that's literally Coriolis what you're describing now.
Well... okay, I'm gonna have to again. There's another complication, I believe, here, which I'm not. I'll go away and think about it more and come back at some stage.
And from the point of view of the shell, it's also the conservation of momentum.
Yeah.
Yes, and that's what Coriolis affects. And the coordinate system that you are using, because when we talk about the coordinate, what's the deflections with regard to, it's where you're starting off. It's not where the target is. And a lot of people focus on the target. I mean, that's
yes, because the target and the shooter, let's take an artillery piece on the ground and the target, and let's say neither of those are in motion. They're both, with relative respect to each other, are fixed. But the moment you fire the shell, it's now free of that reference frame.
Yeah,
it's in its own reference frame now, and so it's got to conserve its momentum from when it left the barrel, taking away drag and wind and all those other forces.
Coriolis effect is literally the change of view from the different reference frames.
As the shell moves through the air.
Yeah.
I think there's another factor here. Well, I'm going
as the shell's moving through the air, it's if you look at it strictly from an inertial reference frame, travels in a straight line, obviously. But when you see that in the path it takes across a rotating frame of reference, it's not straight anymore.
And it has nothing to do with an inertial force. Because if you compare an inertial force with an inertial reference frame, you can also say white horses are white and white paper are white, so white horses are made from paper.
Yeah, good luck finding an inertial force in an inertial frame. It's not there. You're not going to find it. You can look, but it won't be there.
I have a better thing. Parkway and driveway. Do you drive in a driveway or do you park in a driveway?
All right, Gallagher. I know that routine. That's a fact. So yeah, it's a confusing topic. There's no question about that. Yeah, and we try to look at it in a simple way, but there's no really good simple way to see that on anything other than just a rotating disc. Then it's pretty simple. When you throw that when you throw that third dimension in there, things become very complicated very quickly.
I suppose the problem I'm having, Blue, if you fire something horizontally from the equator, firing north, then the cross product is 0. Now imagine there was no gravity and the thing didn't drop and change in angle. Then according to that, there would be no Coriolis force at all, given the equations. Would you agree with that?
Oh, finally. Welcome to Cylinder Earth.
Yeah, I agree.
Right. So, yet obviously we would see something. There's something else going on here about firing, and therefore we're saying there is no Coriolis force firing north to south from the equator, firing perfectly horizontally. Yet obviously we're saying that obviously the in the distance the land will be moving less quickly, and therefore we will see a deflection. So that's the problem I'm having. And I think one of them may be Coriolis, and one of them just may be the fact you've switched reference frames as to what. And therefore, if you just kept the same reference frame from the origin of your firing, there would be no Coriolis effect. Whereas, obviously, if you decide you were looking at a target, then it's not going to arrive there because obviously it's got a greater the velocity east to west is greater at the equator than it is, say, 200 miles in.
No, if it's a very
But
fast
the maths
ball,
doesn't. The maths says that there shouldn't be any Coriolis force, any effect.
well, there won't be. If the projectile is very fast, imagine it will get from the equator to the North Pole or close to the North Pole in 1 second. You wouldn't see it deflect at all.
No.
Well, that's another issue again, because the equation for the Coriolis effect is the velocity times the rotation times 2 with a cross product between them. So if we start getting worrying about velocities as well now, and this is why there is another thing called, I think, the Rossini number, which says how much does this Coriolis force affect constituent, and it depends on the length of the time of your travel. So, for instance, that's why weather systems, although they move slowly, they spend a lot of time moving. So eventually they acquire lots of Coriolis effects. If you fire a laser beam, obviously the Coriolis force, your velocity is very high, then but the time of travel, but the force only has an instant. So although if if you increase the velocity, you increase the Coriolis effect. But if you've got a target that's on the Earth, then it's going to get there very quickly. So that force has only got a very small period of time, or this effect, as a force-stroke effect, has only got a very small period of time to actually affect. So the force is greater, but the time is so small, the effect that it has, and this is why there's something called, I think it's the Rossini number or something, which you then have to work out the length of time over which this happens and the force acting on it to determine what actual effect you actually get from it. It's a bloody complicated subject, and I'm going to read this book. Yes, indeed, the integration forces. That's Clive is.
Yeah, I downloaded it as well.
But the only deflection you will observe will be due to the rotation, the change in the surface velocity, not because the bullet is faster, but the change in velocity of the surface. Surface is rotating under you. That's what happened.
Well, it's not just that. You're getting in the Bob Science Guide type approach. If you fire east to west, the rotation speed isn't changing, yet you still have a vertical Coriolis element. So it's more complicated than that. I'm going to have to do a problem. I'm going to resolve this issue. I say the cross product going horizontally says the Coriolis force should be 0. As I think Blue agreed with me on that. That's what the force says, and if it can maintain that horizontal direction, then the Coriolis force moves up. But we can obviously know that the change in the velocity of the ground is going to cause some sort of effect. But I think that might be down to the fact that you are changing what you're looking at. With respect to where it started off originally, it might not have deviated, but with respect to I'm gonna have to go in. There's a small problem here. That the maths and the intuitive thing is not quite agreeing in my mind. I'm gonna have to go and I'm gonna have to go and read that book that Eric. I don't know if he posted it in the link. Eric posted a link to a book on Coriolis.
Yes.
So I'm gonna have to go and read that.
You fire straight up, you will also have a different type of Coriolis because the atmosphere is dragging and not following.
No, not. This has nothing to do with atmosphere. I'm assuming here an atmosphere-free example.
No. Yeah, okay. Atmosphere free.
We don't introduce the atmosphere in again, because that's just going to cause even more problems.
You still have a different, a Coriolis effect because the distance will be different because
the Coriolis effect should be the same. The Coriolis equations are not affected by whether there's an atmosphere in existence.
No. But I mean, when you fire straight up, the radius will be different the higher the bullet goes or the projectile goes. So you will have also a Coriolis effect.
Yeah, but that's not a factor. The Coriolis effect, the equation for the Coriolis effect, is not dependent on the radius you're going out. It's only dependent on the velocity and the cross product that has with the axis of rotation.
Yeah. So when you're 1 degree or a half degree or a tenth of a degree off, it will have effect.
Clive has done a video on this apparently, but it was out of focus, and I think I moaned about it, and he might do it again. Yes, I'd be very much interested, Clive, if you were to do this, because I'm not complete. I think I've got a slight problem here with the difference between the equation and how you understand it intuitively with firing horizontally at the equator, north to south. Yeah, I have to go and read that book that Eric posted in the link. I don't know whether he put it in the chat. Yeah, I might go and get.
Did because I downloaded from there. Yeah.
Okay, I'll just put it in again just in case people. Let me just get this link.
At least I tried to download it, but I can't read it because it's not.
Okay, I've just posted it in the chat there. This is Eric's link. I haven't looked at it myself. I only saw that I could get hold of it. Let me just try.
Yeah, same link. Same link.
Let's see if I get it.
Did it download it or not?
See if it works. So it seems to be downloading for me.
I got Cloudflare.
Yeah, it works for me. I've got the book, An Introduction to the Coriolis Force.
Good. Okay.
Yeah, it's all downloaded for me. 1989. Let's have a quick look at it. See if it's got. It's a bit old style. Oh, some nice differential equations there. Oh, even some programming. Bloody hell, some programming thing for it as well. Okay, it looks. I mean, it's reasonably long.
Yeah, now I have it. Thank you.
Okay, it's giving some basic. It's got a basic program in it. Oh God, in as well. But it seems to be okay. There's a reasonable amount there. It seems to go into the detail you might want to understand. Rotating coordinate frames, bit more code. So yeah, hopefully I'll I should read that.
Code I get more than I'm very heavy dyslexic, so.
Right. Numerical. Okay, I'm going to go and yeah, that looks like a reasonable book with some basic programs in it as well. Quite a lot of them. And quite a lot on spherical coordinates and cross products and differential equations and some exercises. Ooh,
cool. Cool.
Okay, right. So that book of Eric's, yeah, yes. So there's some to chew on.
All right. Yeah. Exercise.
Oh, it even allows for the rotating of Blake Earth as well. Okay, excellent stuff.
Hey, Rumpus.
Hello.
How you doing?
Oh wow! It's a basic program in it.
Yeah, exactly. That's what I was saying.
Yeah.
Oh, George. Well, I'm having a bit of a confusion, George, because I'm having a problem with Coriolis in the fact that the math says one thing and the intuition says another. It's a problem that's been worrying me for over a year now, and it's sort of come to a.
Why haven't we ever discussed this then?
No, I missed my Commodore
You're
64.
too proud.
I can tell you everything, George.
To have an engineer correct you.
No, that hasn't happened yet, fortunately. No, I must admit, I don't tell you everything, George. I must say it's something that's troubled me, but I've just assumed it was something I was not fully understanding. But I'm not so sure now. It's something that's been worrying me for a couple of years now that I haven't quite resolved in my head. But perhaps Clive is going to do a video on it, perhaps, and then Clive Wells is in the chat who's done a video on this, and he might.
I just took a quick look at that book, Introduction to Coriolis Force. Equations 4.2 and 4.3 are wrong.
Yeah, but the book makes me miss my Commodore 64.
Yeah, you should be able to use your Commodore 64, yeah.
Yeah, but when my house was rebuilt, I was at sea. My mother actually helped clean up the attic and throw out my Commodore.
Well, you can probably run some basic. There's bound to be some basic you can run on a PC. What was the equation, George? You said was it 4.2 or something? Did you say?
4.2 and 4.3.
Right. Yes, because George and I have also been trying to work out another problem. What was the thing we were trying to sort out? Oh, the Eötvös effect. Yes, that was right. We were trying to sort out whether, because you always hear about going east to west to get the Eötvös effect, and George and I were trying to resolve this in terms of any motion, whether or not you could get the Eötvös effect. You could measure it going at any angle, and it actually turns out to be rather complicated.
Oh yeah.
As you'd expect, and so George and I didn't quite resolve this fully. We thought we had solved it at one point. George thought he'd solved it at one point, and then
it was more than just trying to resolve trying to explain the Voltos effect as being one of the components of Coriolis.
Yeah. And we didn't quite. We were trying to work out a simple equation that would say this is what the Edwards effect should be going at.
We got it, but we never addressed
No,
it.
I didn't think we
got off
resolved it.
onto something else, but I managed to get it in spherical coordinates.
Yeah, but I thought there was a problem with that. Okay, perhaps. I mean, I thought we.
Well, we did, but then later on I went and did it rigorously and managed to resolve the issue, and I informed you of it, but we never did.
Yes, and
I think it was we started having flooding issues or something here, and so I never really addressed it with you.
You didn't, yeah. We left it undone. Yeah, well, if you want to get back to that, perhaps yes, that'd be interesting.
Oh, by the way, my comment about equation 4.2 and 4.3, I was just pulling your chain. I wanted to get you to look.
You devil, George. See you back again. You're my nemesis, aren't you?
I see that Blue had a super chat, so.
Yeah, I need to read this one out for sure. Bjorn Kamitz, 500 SEK. Thank you so much, Bjorn. Says, as usual, great stream. It's always good to connect with old friends and establishing new ones. But I'm confused to why Flurfs still think they have the globe in the bag. They're still beating the same dead horse. Yeah, well, I've had the dead horse up on the screen now for a while, so that's exactly what they're doing, beating the dead horse. Bjorn, thank you so much. I really appreciate it.
I mean, the problem is they're stupid, and they want to believe in something, and everything we tell them, as I say, they've got this shield of stupidity and ignorance. We can't get through to them except with things like evidence, science, logic, reason, maths, and all those things they can fend off by being stupid and saying, I don't understand. And we've got QE, who doesn't understand the difference between relative velocity around the Earth and 15 degree per hour drift and what Coriolis is, and they've got those two things completely confused. And getting through to these people, particularly as Sean was pointing out earlier, when they don't want to understand, they deliberately want to misunderstand what you're saying, or they just want to reject science as being silly, as we've had QE spouting lots of that science-denying crap earlier. And when they've got this attitude, you just, if they want to believe for really different reasons, like religious, or they don't like society or science, they can't understand science, therefore they reject it, then they're going to reject every explanation you give to them. They're silly, stupid people with a delusion problem for some character defect or intellectual defect.
But you have to remember, Rumpus, where Quantum Eraser gets us is that he is a religious fundamentalist, and he tries to explain everything from the Bible.
Yep, I mean, he's got an argument. He did. I mean, one argument I saw him post in some comments recently was about the necessity for being an observer for reactions for the collapse of the wave function, and he said therefore you need God, and he cited an article in Scientific American, which I'm currently processing, which claims that human consciousness, which claimed that human.
Sorry, go ahead.
Which claimed that human consciousness is required. And indeed, when I was studying physics at university, I had read these books like Schrodinger's cat. They talk about consciousness being required to collapse the wave function, which I thought was utterly, utterly ridiculous. And I thought, how could intelligent scientists think this? And of course, this has been rejected since then. I think in the last 20, 30 years or something, 20 years, this has now been regarded as tosh. But unfortunately, QE is now citing a Scientific American paper dated in 1979, where some chappie, I think it's a French philosopher actually, is trying to say that you have to have a human consciousness observing things to cause a collapse in the wave function.
Well, anyway, it was about 2 years ago, I think. Quantum Eraser was on Oakley. Oakley dedicated several shows to Quantum Eraser, if I remember right. And Quantum Eraser was doing this Bible study for about, 3 or 4 Nathan shows, and going through and showing Nathan where the second law of thermodynamics was discussed in the book of Genesis.
Yeah, I mean,
really?
I mean, I think half of flatties are religiously inspired to be flatties, at least half. Yeah, he's one of them. God, bloody! I'm getting hassled by Repose and Man now, saying I'm boring people to death with physics. Yeah, well, so. Yeah, I think Yeah, the trouble is well, these complicated things that require a bit of effort with maths and things. I mean, they seem a bit boring and tedious and involved because, unfortunately, the real world is very complicated, and understanding it requires a bit of effort, really. And that learning things is never terribly exciting. But it can be fun if you spend a bit of time learning celestial navigation, then saying, "Oh, I know how to get where I find out where I am if I'm in a boat or by myself in the middle of the sea, armed with a clock, timepiece telling me what my time is, and a sextant. I can work out where I am." So you can do some fun things when you do understand some stuff.
Well, you need a little bit more than only a timepiece and.
Now hold on. Do you though? If I've got a timepiece and a sextant, surely if I'm in the middle of the sea, never just been transported there, surely I can work out where I am. If I make observations of where the south, I can work out where noon is, the solar noon is with respect to time, then surely I should be able to do that.
Oh, you also need a map.
No, why do I need a map? If I know...
almanac.
No, I don't know. You only need those things if you want to do the line of position you want to do. But if you just say, right, I'm going to take some observations of the sun. I've got the whole day to play with. I'm in the same place. I can then work out where solar noon is. I can then work out the time is. Then that I should be able to work out the longitude from that, and I can work out my latitude, obviously, from the sextant, having worked out when solar noon is. Although that's quite tricky to work out when the sun is at solar noon, surely that's enough for you to from standing. Although it's not, I mean, people have a problem with this because, of course, where solar noon is quite tricky, unless you've got a sort of whole day to play with. And if you're moving around, it makes it more difficult. But if you're in the same place, then surely, Captain, you can work out where you are from a standing start without a map.
You can actually guess from the time, location, and the sunrise, and the height of one of the rotation star points, or the rotation point of southern rotation point or Polaris. You can have a good guess where you are, and then well, you need a piece of paper to actually draw it out, because you can measure.
Well, do you though? I mean, I know there's a problem because I think, are you worrying about the fact that circles of equal altitude are crossing one another, and you can't draw those properly on a flat map? Is that what you're worrying about?
Those too far away.
But if I can work out what the time of solar noon is, I don't need to do any of that, can I? Providing I've got the whole day to play with.
You get a guess position then, and from that guess position, that's actually how we do it at sea. You take your guess position or your last position, and from there you actually take the measurements you took from the stars, and with the calculation, it's the difference between the distance from the guess position to the GP and the official distance to the GP. That's what you get. At that distance and that direction, you actually draw out, and that's how you get your position.
But
it's not that we don't use the GP. We actually use the difference between the calculated position
if I can work out where solar noon is reasonably accurately, and I have a timepiece, and I know that in GMT, and then I can use the sextant also to then measure the altitude of that, then surely that's enough to tell me where I am. And I therefore, even without having an almanac, without having a map, I've then worked out my latitude and longitude.
Really? Do you know the sun altitude for every day in the?
Yes, you need a calendar as well.
I was just going to say.
No, not just a calendar. I'm supposing you have a calendar. Do you know what the sun altitude at each day?
Well,
yeah, that's true. Okay.
May I?
No.
You have, can get by knowing GMT. Yes, we are saying a GMT and date without hesitation. And one additional information that you need to know is the declination of the sun on that date.
Yes,
and that doesn't change grossly from year to year. So it can even be an old. So if you know the declination of the sun for that date, and by timepiece, you know GMT, that's GMT and date. Yes.
Yes.
And if you're stationary, or at anchor, on an island, yes, you can observe. You can determine a precise solar noon, gives you longitude, and a precise vertical angle, and you have the latitude. Without a GP, without a dead reckoning position, it can be done from scratch. Now, using your dead reckoning position or your best estimate and LOPs, that's expediting, yes, and then you're making progressive because you never really were totally lost. But from totally lost, and you can observe the sun through one solar day with the additional piece of a declination for that date, which is not a big complicated table, and a GMT chronometer with date, you can work it out from scratch.
Yeah,
If you do not use the tables, what Rumpus is suggesting, you actually only get your you only get your guess position.
No, wrong. Sorry. Nope. Wrong.
No.
Sorry. Nope. Wrong. Sorry. I'd refer to the Ordnance Survey UK's book on navigation and topographic surveying. Yes. You observe the sun as it's rising, and you note a time when it's crossing, say, 45 degrees, and you continue to observe the sun when it peaks, and you don't really know when it peaks because it flattens out, and then you observe the time when the sun crosses 45 degrees while setting. The average of those two times is a precise local astronomic noon, and your peak altitude is your peak altitude, which is kind of like using the equator as your GP, and you know the declination for that date. There is that little piece of information you need to know, your declination of the sun for that date, and or if you're using Polaris, which
that's what I mean. If you do not have that,
correct. Yeah, granted, admitted. Yes.
Yeah, I didn't.
If you do not have that, you can use you can use the sunset and sunrise, estimated times, and everything, but then you get your guess position.
Well,
but
if you're using sunrise and sunset is your least. That's crude, but that's if you don't have a sextant. But if you have a sextant and you can measure when it's at a nice healthy altitude, like 40, 45 degrees, and you can record the time crossing 45 degrees rising, crossing 45 degrees setting. Yes, then you're not getting a guess. You're getting a cracker, measurement.
Yeah, but there still will be a difference, and you still need the almanac to actually get the corrections.
Just for declination, in that scenario, just for declination.
Yeah, but you will have a closer guess. But for the declination and everything, for your actually position, you still need the almanac, and you still need the tables, and you still need.
I don't see why.
And if that table only included a single column of declination for the date, you have your chronometer.
No, the tables are not dates. The tables, I have the tables here. They're tables from a couple of decades old, and they don't change. The tables are
annually.
Just
yes, annually declination does repeat without it, very much, and we do have leap year, subsidence in there. So yeah, you do need a good, up to date one or some formulae to carry you through the calendrical years. So yeah. But if
Captain, when he said date, he didn't mean a year. He said a date just for, in other words, what day of the year you're in. That's what he meant by date.
No, date is day of the year. Yeah, that's what you need with the almanac. But the other one is the correction tables, and the correction tables don't change. The correction tables are actually the fragment of the dip, the refraction, stuff like that is in it, and
but you don't need that
doesn't change.
I suppose there is a slight error, of course, of the refraction of the sun. I suppose.
Yeah.
No, actually, I did overlook one additional thing that he accurately pointed out. Equation of time, because you could have plus or minus 15 minutes on local solar noon to Greenwich. Granted, I yield on that. So declination and equation of time. Now you can calculate equation of time, or you can come off a simple sine wave graph and get that well enough. But you're gonna know where you're at pretty damned well without using GPs and LOPs and a dead reckoning position.
Yeah, I forgot about the equation of time. Yes, that's the trouble with it. Its bloody sun doesn't move around perfectly uniformly through the year. Yeah, that's a tricky one.
Yeah, there's also a point.
But that would be 15 minutes or so, which could be is it several miles without a doubt.
Not completely correct. We have to calculate when you do celestial navigation. You have to calculate the exact time, and it's not the hour shifts, but actually on the second. So you have to calculate it differently. But
and to be clear, if you are fighting clouds, you just need 3 positions of the sun and the more complicated maps. But with just 3 positions of the sun at random times of the day, separated by multiple hours, you can still get the solution. It's just more calculation comprehensive.
Yeah.
One thing, Larry, but when you're talking about as you don't know exactly when you're doing it, the position of the sun, presumably you'd have to take an angle measurement, say every few minutes or something during the day and then work out which one of those was the solar noon later.
Okay, yeah. Like I said, as it crosses 45 degrees, right, up, you record that time. And yeah, you pay attention, and you don't have to take it like every minute, but you'll see when it's slowing and comes to a near stop. And then you have like 10 minutes where it's not going to significantly change, right? So yeah, you have to keep an eye on it, but you don't have to, for 4 hours, do it every 10 minutes.
Now, on my last trip, I did. I didn't do solar news, but I did a lot of 3-star navigation,
Yeah, LOP,
4-star navigation.
line of position. Yeah, line of position, which is standard. Yeah, and a nice little piece of graph paper assists in that because that reduces your calculation.
No, I did it on a chart every time, but that doesn't matter. The only thing what I actually noticed most is if I could do a lot of views in a very short time, then the position was more correct than I did with calculating with what I presumably direction I did and presumably speed I did, because of course that's not constant. So yeah, it was fun to do. It was especially fun to do actually because I was on one point. It was very close to the equator, so I could do sight of stars on the south part of the equator pretty easily, and I could see the Southern Cross, even though I wasn't on the south part of the equator yet. But it pointed to the rotation point that was below the equator. Yep. So yeah. Well, it was nothing new to me actually, because I'm doing this for 22 years now, or 23 years already. But
one time, a pilot that I worked with, he was curious about sector navigation, and we didn't have a good instrument, but we had a pretty nice inclinometer, and I attached a laser pen pointer to it, and I took the vertical angle to about 8 stars one night in rapid succession, and leaning on a piece of software, keyed that in. I got within 1,000 feet of GPS.
Yeah, it's cool. I was lucky that it was a harbor tug. It was a small tug.
I had to bring from Vietnam to Portugal. But Portugal has some old-fashioned rules, so was we had a section on board, and normally you don't have it, but this was a really, really, really nice carbon cloth, really good one. I calibrated it a little bit because it wasn't calibrated yet, but and then I did well, I have good weather. I did measurements. So in the 2 months, I did about 16 or 17 measurements. It was nice.
Well, guys, we've been at it 3 hours and 10 minutes or thereabouts. And I think I'm going to say good night to the YouTube stream. And we can hang around in here and talk as long as you guys want to. But at this point, I want to thank everybody for being here. It's been a fun afternoon, I think. We have certainly beaten the Coriolis dead horse, even deader, at this point. And maybe we'll do this again real soon, like tomorrow. I don't know. We'll see. I'll let you guys know. So
thank you.
Yeah. Good night, YouTube. See you guys later.
Yeah, and I want to thank you, Blue,